And then we're also going to live stream onto YouTube as well for those that, there we go, that didn't get registration in time.
Okay, so it is 3 o'clock Eastern. Brianna, can you take a look at the participant list and see how many had registered? And if we have more or less all of whom who had registered online.
Let's give it just another minute or so.
Sure.
And then for those who are online, we will be using the Q&A tab for any questions that you have. The chat is disabled, as is the raise hand. So any questions or comments or concerns, please put those in the Q&A. And then just a couple other little housekeeping items. We do not typically provide certificates of completion for the courses. If you do require that, you can reach out to me, Brianna Moreno. Um, you should have gotten an email from me when you registered. Again, please use the Q&A section, and slides will be provided later on this week, as well as the recording. And then Psyched, I think you're good to go ahead and begin.
Thanks a lot, Brianna. Welcome everybody to this course on the CQN's winter school this year. My name is Saikat Guha. I'm the co-director of the Center for Quantum Networks. We are a center that was established about 5 years back. And the objective of the overall center's research is to build the quantum internet, to be able to communicate qubits from one point to another with high fidelity and high rates. And this winter school was instituted to get people up to speed on the underlying concepts of quantum optics, quantum mechanics, classical network theory, and quantum devices, for you to be able to accustom yourself with the fundamentals to, if you wanted to get into this area of quantum networking. So we are in the third year of this winter school, and I would really appreciate any feedback through the feedback form at the end of this course and the other courses in this series. A couple of word of acknowledgements. First, to Professor Mike Raymer, who is the person who is behind this winter school. He's one of the best educators in quantum information sciences, and he's at University of Oregon. And Brianna Moreno, who's our program coordinator for CQN, and without whose help and support, this winter school would not have been possible. This particular course, I'll be joined by my PhD student, Prajit Dhara. He's a final year PhD student at University of Arizona, currently at University of Maryland. And he will be teaching one of the 4 sections of this course. This course is titled Modes, States, Transformations, and Measurements. We listed this course as a level 3 course in this year's winter school, which means that we are going to assume that you are either familiar with or are enrolled currently in an upper level undergraduate curriculum in electrical computer engineering or physics or similar, and have seen some level of electromagnetic theory and ideally some quantum mechanics in your studies so far. But even if you have not, having had some basics of probability theory and linear algebra will definitely be very, very useful. And we are going to assume that you have seen those. The objective of this course is to accustom you with the concept of modes and the quantum state of a mode. And we are going to start with a very gentle introduction to classical optics, understanding what do we mean by an electric field of light. What's the most general way to talk about the field of, and then we are going to go into discussing what are other states of electromagnetic fields that are not describable within the realms of classical theory. And then towards the end of the course, we are going to have a little bit of fun working with both classical states of light and quantum states of light, manipulating states of light using things like beam splitters and phase shifters and detecting them. And hopefully towards the end of the course, you will have some flavor of applications where non-classical states of light have some improved performance in certain areas of processing information that is embedded in photons. All right, so let's go ahead and get started. And I'm going to begin by saying that you should have a pen and paper ready for this course. All the courses in the winter school have what we call poll questions. So Brianna is going to pull up a Zoom poll with options like A, B, and C, and D. And then I'm going to pause for, say, 60 seconds or so and have you work on a problem when we flash a problem, and then you will choose the right option for your solution. So it's very important that you actively engage in the process, and also feel free to go ahead and type any question you may have in the webinar chat. And both myself and Prajit, we are going to try to answer those questions live as they come in. All right, so let's go ahead and get started. This is the outline of the course. So we'll start with describing what we mean by a mode of an electromagnetic field. And then section B, we're going to talk about classical states of light, and section C, we are going to talk about quantum states of light. And then section D, we are going to look into some applications, including things like telling apart between different states of light and its applications. Okay, so let's start with the part A. The word mode is used in the context of optics and electromagnetic theory to describe a shape, a physical shape in space and time. Um, by shape, I mean a functional form. For example, phi of r comma t, where r is x and y. So it's x and y are two orthogonal transverse coordinates, and t is the time coordinate. And nu takes one of two values that corresponds to polarization, the direction of the oscillation of an oscillating field that takes one of two orthogonal values. So when I write down a mode function, phi of r comma t, there are two things I'm going to assume. The first is that it's normalized. Normalized means that over the extent of space and the time over which the function is defined, if I were to take this function and take a magnitude squared of that and integrate that over that extent of space and time, I'm going to get 1. And the second thing is that if I have um, uh, a mode function that is uh, orthogonal to another mode function, then if I take the product of the mode function with the complex conjugate of the other and integrate that over the same extent of space and time, I'm going to get 0. So before we go ahead, I'm going to start with a very simple exercise to start with. So the exercise will be for you to consider this mode function, phi of t. So it's a function of time. So a is a scalar value. So a is some variable. So from 0 to t is where the function is defined. And I would like you to find the value of a such that phi of t is a properly normalized mode function. So again, a recap for a normalization is that if you take the magnitude squared of phi of t, and I'm going to let you assume that a is a real number, and integrate that over the extent of, in this case, time that this function is defined, that you're going to get 1. So why don't you go ahead and take, say, 60 seconds or so and try to find the value of a. And here are the 4 options. And Brianna, go ahead and pull the poll question. So for those of you who are still working on the problem, the first thing I would do is to sketch out the magnitude squared of phi of t. And because phi of t is a real valued function, the magnitude squared is just the square of the function. Okay, so for example, the square of the value of phi of t over here at 0, right after 0 is going to be a squared. And the value at t over 4 is a plus a over 2. So that's 3 over 2. And so the value of phi of t squared is going to be 3a over 2 whole squared. So sketch that out. And then you're going to integrate that from 0 to t and set it to 1. and then solve for the value of A. So there are about 40% people who have worked out. I'm going to mute myself and wait for another half a minute or so, and then be back.
I'll go ahead and end the poll now.
Okay, so about 60% of people have participated. I would really urge people to actively participate in problem solving because it will make for a much more rewarding experience through this course and any of the other courses. So let me go ahead and flash the answer. So the correct answer is D. And let's see. So a lot of people came up with A. And if somebody wants to write down your solution or comments as to why you got A, I would appreciate it. But looks like the second most popular answer was indeed D. So what you would do is that you would just take the square of this function. So if I were to take a square of this function, it's going to look very, very similar. At 0, the function is going to be A squared. And then at t over 4, the value of the function is going to be 3a over 2 whole squared. So this value will be 9a squared over 4. And then it's going to stay like that, and then back over here, and then at t. So now you're going to integrate it from 0 to t and set it to 1, and you're going to get the value of a equals to that. Okay, all right, so let's keep going. So a mode is just a function. And a mode needs to be normalized over the extent that it has been defined. Okay, so let's talk about Fourier transforms. And this is another concept that I'm going to assume that you have seen in some form. Now, we are going to consider the simplest possible mode function that you could think of, what we are going to call the flat top temporal mode. And in the subsequent slides, we are going to also give this mode another name. We are going to call it the pixel mode. So the flat top mode is a mode that has a constant value over a fixed duration of time. Now, if I wanted to define a mode function that has a constant value over the fixed duration of time 0 to t, it has to be 1 over square root of t. Why? Because if I squared that value and integrated that over 0 to t, I need to get 1. So the moment I have decided that the mode function has to have a constant value over 0 to t, I have already determined what that value is. So phi of t is 1 over square root of t between 0 to t, and it is 0 otherwise. So we are going to call this the flat top temporal mode. The Fourier transform of a time function is defined by this integral. You multiply the function phi by e to the minus 2 pi I f t and integrate that from negative to positive infinity in time. And the function that you get in f, where f is a frequency variable, is known as the Fourier transform of this time function. And we are going to denote the Fourier transform by a capital letter. So cap phi of f is the Fourier transform of little phi of t. And you can always go back from the Fourier transform to the original function, modulo certain smoothness conditions of the original function. But you can multiply that Fourier transform by the same exponent without the negative sign, and this time integrate over the frequency variable, and you will retrieve the time function. So it's called an inverse transformation. The frequency variable has the unit of hertz, and sometimes we are going to use frequency in radians, omega, which is 2 pi times f. Now, the reason we take the Fourier transform is because we want to look at a function sometimes in terms of its spectral component, in terms of its Fourier components. If you look at this function over here, phi of t, the inverse transform equation, I have expressed phi of t, the time function, in terms of a, you can think of this as a continuous sum of oscillating sinusoids that are oscillating at a frequencies f. And this phi of f is a coefficient that is multiplying that sinusoid oscillating at frequency f. So if you look at the value of phi f at a certain value of f, what you are looking at is what content of that particular oscillatory frequency exists in my time signal. Okay, so if you look at the Fourier transform of this particular function phi of t, it has a name. It is known as the sinc function. I thought I had the functional form of sinc. I forgot to put it in here. So sinc of x is sine of pi x over pi x. Okay, so it's a sine divided by the argument. So this function has a width that is roughly equals to 1 over t. Meaning if I were to stretch out this time function, the Fourier transform is going to shrink. And if I'm going to shrink the time function, the Fourier transform is going to expand. And this is a property that is true for any function. So the spread in the time is inversely related to the spread in the frequency. The spread of a function's Fourier transform in frequency is often termed as bandwidth. It's roughly equal to the inverse of the spread in time. Now, there's a very important property of Fourier transforms that I have written over here in the bottom, that if cap phi f is the Fourier transform of little phi of t, then if I shifted the time function to the right by an amount t naught, then the Fourier transform is given by the original Fourier transform times an exponential, which is e minus 2 pi I f times t naught. And if you have taken any course in linear algebra or probability theory or anywhere that you have learned Fourier transforms, you must have derived these equations. A very simple way to see that you go ahead and substitute phi of t minus t0 in this equation over here, and then write this integral. And then go ahead and substitute t prime for t minus t0. And then rewrite this t over here in terms of t minus t0. And then if you redo the integral, you will get a pi f term, and there will be a constant exponent e to the minus 2 pi I f times just the t0 portion that's going to come out of the integral. And you're going to get phi f times e to the minus 2 pi I f t naught. Similarly, you can apply the same thing on the inverse transform. If you shift the Fourier transform to the right by f naught, that's going to multiply the time function by 2 pi I f naught times t. Okay, so let's see this in action for a specific function, set of functions. Before we do that, there's one interesting property that we are going to use later. It's known as the Parseval's theorem. So if I were to take the mode function phi of t magnitude squared dt and integrate that from negative infinity to plus positive infinity, it equals the magnitude squared integral for the Fourier transform as well. This relationship is known as the Parseval's theorem. Now, in this case, since these are, sorry, what happened here? Yeah, I think I lost my screen. Oop. I think what's happening is that when I'm trying to click on the Q&A, I'm losing my screen. So, Brianna, can you see my screen still? Or is it going back and forth?
It's going back and forth, Sakat. I'll answer the Q&A unless there's some
I see.
question.
Okay, so I think
Yeah,
I'm going to just then avoid clicking on the Q&A because
yeah.
it's just getting, I'm losing my screen. Okay, thanks, Prajeet. So the Parseval's theorem is simply saying that the magnitude squared integral is the same in time or frequency. And if it's some mode function, then the magnitude squared integral has to be 1. So it means that it's 1 no matter which way you do the integral. Okay, so let's look at orthogonal modes. So I mentioned this in the first slide that if two mode functions are orthogonal, what we mean by that is if you take the first mode function and multiply that by the complex conjugate of the second mode function. And again, integrate that over the space and time extents over which the mode functions were defined, you are going to get 0. Now, the polarization index, nu and mu, we are going to drop for most of the course, but just for your information, because the polarization mode indices are takes 2 values, then the 2 mode functions will be orthogonal regardless of what their spatial and temporal modes are, if nu and mu are not same. Meaning if there are 2 mode functions that have orthogonal polarizations, say a linear polarization in one direction, it's orthogonal direction, or a circularly polarized mode function and a counter circularly polarized mode function, then no matter what their space and time function looks like, they are going to be orthogonal. But as I said, we are going to drop the polarization subscript for the rest of the course, which means that I'm going to assume that all the mode functions we are going to talk about have the same polarization, which will mean that for 2 mode functions to be orthogonal, this integral has to be 0. Okay, so now one question that arises, which was addressed by David Slepian through a series of papers back in the 50s, actually, that how many orthogonal modes can we fit into a time bandwidth product? So I mentioned to you in the previous slide is that if a time function has an extent capital T, then its Fourier transforms spectral extent, meaning however far the most of the content in the frequency domain that cap phi of f lives, and we call that capital W. We said that T and W are inversely related with each other, right? But we could now ask that, well, if I gave you a T and a W, okay, so if I said that I wanted you to write down orthonormal modes, orthonormal meaning mode functions that are mutually orthogonal with each other, and each one of them is normalized, of course. So phi k of t from k equals to 1 to capital K being an orthonormal mode set means that if I pick any 2 functions from that set, they are orthogonal to each other. And their respective Fourier transforms capital phi k of f. And again, by the extension of the Parseval's theorem, if 2 mode functions, say phi 1t and phi 3 of t are orthogonal in time, then phi 1 of f and cap phi 3 of f will be orthogonal in frequency. So if I were to ask a question that what's the largest k, meaning how many orthonormal modes can you write, such that they're limited in time in t seconds and roughly limited to w hertz, meaning all of the functions little phi t are roughly contained in 0 to t, and all of the Fourier transform functions cap phi of k of f are roughly contained in w hertz, capital W hertz. Why do I say roughly? Well, because I just told you in the last slide that if a function is limited in time, like I showed you that function, the flat top mode was limited in time. And if you remember the frequency domain function, the Fourier transform, that sinc function, it went forever from negative infinity to plus infinity in frequency. And by the way, and that's also something that is true no matter what time limited function we are looking at. If a function is precisely limited in time from 0 to t, then its Fourier transform always is completely unlimited. It goes from negative infinity in frequency to positive infinity. But we are saying if you wanted to say contain most of the spectral content of all the functions in W hertz and most of the temporal content in 0 to t, how many functions can you write down? So this particular question was answered by David Slepian, and he found a set of modes that have this property that you can pack in the most number of orthonormal modes that have this property. And the maximum number of modes that satisfies these conditions is roughly equal to W times T. And this reason is why people call W times T the time bandwidth product. The time bandwidth product is a thing that if I have a spectral content in one direction that is W hertz and temporal content in T seconds, then W times T is roughly the number of orthogonal functions in time and hence frequency that can reside in that product, in that window. Okay, so to get a feel for the time bandwidth product, we are going to look at what we will call the pixel modes. And we are going to use this word from here on, from this slide on. So let's go ahead and define what we are going to call pixel modes. So pixel modes are these set of modes. So I'm going to take a time extent of 0 to t, and we will define capital K time functions, and each one of them is limited in time. The first function phi1 of t is limited from 0 to tau. The second one is limited from tau to 2 tau, and the third one from 2 tau to 3 tau, and so on. And each one is a flat top mode. Now, if you look at the first function, we just said that if you had decided that the mode function is a flat top mode from 0 to tau, the value of the function has to be square root of 1 over tau, because it has to be a properly normalized mode function, 0 from over here to here. So if you square it and integrate it from 0 to infinity, you're going to get 1. So all of these mode functions are properly normalized. And it is pretty easy to see that if you pick any two mode functions from this set, they are orthogonal. Why are they orthogonal? Well, because you just take a product of any two of these functions, you're going to get 0. You don't even have to wait to do the integral. You just take a phi1 of t and multiply that by phi2 of t, you're going to get 0. So the integral of 0 over minus infinity to plus infinity is obviously also 0. Now, another thing to note is that each function is time limited, but each of these mode functions fills up the same bandwidth. Okay, so how do we see that? Well, so if you look at the first function, its bandwidth is roughly 1 over tau, right? Because if you take this flat top mode, take the Fourier transform, you're going to get that sinc function. And just like we saw before, the sinc function will have a width which is roughly equals to 1 over tau. But then if you have that spectral width 1 over tau for the first one, and if that's the same spectral width for all of them, okay, then you can pack in capital T divided by tau, which is equals to W times capital T number of modes. Now, why do all of these functions have the same spectral width? Well, it's easy to see by taking the Fourier transform. So if you take the Fourier transform, so recall that shifting in time, meaning you have to multiply the Fourier transform by this e to the minus 2 pi I f times t0. So that's this. If you write down these functions, let's take a look over here. So if you write down these functions, phi2 of t is phi1 of t, phi1 of t minus tau. Phi3 of t is phi1 of t minus 2 tau, and so on, right? So phi k of t is phi1 of t minus k minus 1 times tau. So if you were to take the Fourier transform, if you look at this t0, that t0 is k minus 1 times tau for phi k of t. So the Fourier transform will stay exactly this phi of f is exactly the same. So this is the Fourier transform of the first function, phi1 of t, square root of tau times sinc of f tau, and you multiply that by this exponent. But if you take the absolute value of this Fourier transform, this phase portion goes away. So the absolute value of the Fourier transform is the same no matter what k is, which means that the spectral content, capital W, is the same for all of them. So they all occupy the same frequency, same frequency content in hertz. And because they all occupy the same frequency content in hertz, you can, and roughly speaking, because this, as you can see, this goes from negative infinity to plus infinity. So roughly speaking, W is 1 over tau. And hence you can see from this equation that if W is 1 over tau, you can back in roughly W times T number of orthonormal modes. The phase, on the other hand, which if you were to plot the argument of phi k of t, which is this 2 pi f times k minus 1 of tau, that obviously becomes more and more wildly oscillating as k increases from 1 to capital K. But the magnitude of the Fourier transform stays constant. Let's look at another set of modes that also fills up the exact same time bandwidth product. And we are also going to talk about these modes in the context of our course today. So these modes are called the Walsh-Hadamard modes. And this time, each of the modes will fill up the same time, 0 to t. So the previous example, each mode functions, they filled up distinct, non-overlapping time extents. But this time, for the Walsh-Hadamard modes, we are going to have these mode functions, they all will fill up the same time extent 0 to t. In the previous example, all of the mode functions have the same spectral content, but different temporal extents over which they lived. But here, they all have the same temporal extent over which they live. So it's a little bit hard to see why they are orthogonal, but it is not too hard to do the math. So if you take psi1 of t, for example, this mode function, and psi2 of t, which is this mode function, and if you want to see why they are orthogonal, you'll multiply psi1 of t by psi2 of t and then integrate. Right? So if you multiply psi1 of t by psi2 of t, you're going to get basically psi2 of t, except that this term is going to become square root of 1 over tau times square root of 1 over tau. So it'll be 1 over tau. And if you integrate it from 0 to capital T, this is 0. So this is negative square root of 1 over tau over here. So you're going to get 0 when you integrate it from 0 to capital T. And same is true if you multiply this function by that function and then integrate, you will get 0. If you take any two functions from this set, multiply with each other, and over 0 to t, you will get 0. By the way, these functions, the fact that they are orthogonal, these functions also find use in many practical uses. For example, if you have heard about the CDMA standards for cellular communications. So they use these Hadamard Walsh modes as what they call chip sequences. So if you have multiple users who are trying to communicate on the same channel, and you wanted to add all of their information on one signal while say communicating to the from the base station, you can have each of these Hadamard modes carry different signals and add them up. And because they are orthogonal to each other, they can be separated later on. And we'll talk about separating orthogonal modes a few slides later. Okay, so if you look at these modes and take their Fourier transform, and this time I'm going to leave it as an exercise for you to work out the Fourier transform. It's very easy to look at the Fourier transform for example, psi2 of t. So this one, we already wrote down the Fourier transform for this. And I see there's a typo over here. This should have been capital T, not little tau. So this goes from 0 to capital T. So this will be 1 over square root of 1 over capital T. And all of these will be square root of 1 over capital T. Okay, so when you and we'll fix these typos that I'm identifying right now before we distribute the PDF. So if you take the Fourier transform, for the first one, you will get a same function, and its bandwidth is 1 over t, as we discussed. The second function, if you take the Fourier transform, this time the bandwidth will come out to be 2 over t. So the bandwidth is twice as much. This one, the bandwidth is 4 over t, and so on. So I'll let you work it out, but intuitively, why is the bandwidth of psi2 of t larger than psi1 of t? Well, psi2 of t is more oscillatory. Psi3 of t is even more oscillatory. Okay, so meaning if you were to write down its frequency content, it will have more coefficients at higher frequencies. So it will have a larger frequency spread. So all of these functions, they live in the same time window, but they span higher and higher frequencies. And again, we can work it out that you can pack in roughly t times w number of orthogonal modes in the time bandwidth product. Okay, so now that we have talked about mode functions, we are going to take the next step and talk about electric fields or the state of a light that is excited in a mode function. Before we go there, if there are any questions that are addressed, Prajit, that you think that I should comment on, that's on the chat window.
Some questions were regarding the orthogonality of the functions I answered. Somebody asked, is this the same as Shannon's theorem?
So I don't know which Shannon's theorem are we talking about. So if you're talking about the Shannon-Nyquist theorem, if you have read the Shannon-Nyquist theorem, it has to do with sampling. We did not talk about sampling, but for those who are interested, the Shannon-Nyquist theorem says that if I have a signal that is band limited to W hertz, okay, it has its frequency spread is W hertz, and you are asking if I were to go back to the time signal and say that I want to perfectly represent that time signal, how often should I collect the values of that time function? Meaning, how often should I sample that time function such that even with those finite number of values of those samples of that time signal, I'll be able to fully reconstruct the time signal. And that is answered by the Shannon-Nyquist sampling theorem. So it's related to what we were talking about, and the derivation of the Shannon-Nyquist theorem does involve Fourier transform theory, but we did not talk about that, and we'll not talk about sampling in this course. Anything else? So I see a couple more questions in the chat window. All right. So I would say let's forge ahead into part B. So part A again, just a quick recap. We did not talk about light, quantum, or optics at all. All we were talking about are functions. And now I would like you to think about a set of orthogonal modes as a set of buckets. Okay, so when we talk about a state of light, we talk about electromagnetic field. What we're going to do is that we're going to assign a complex number to each one of those buckets. So if you have a set of, say, two orthogonal modes, and I want to write down the state of the field, I'll express the field as a sum of a set of orthogonal modes, and each orthogonal mode I'm going to weigh by a complex amplitude. And that will be the story that will unfold through part B. So let's go ahead and get started with the most simple concept, but a very, very profound concept in optics, that of a coherent state of a mode. So let's go ahead and consider that same flat top temporal mode that we talked about earlier. Phi of t is 1 over square root of capital T from 0 to capital T and 0 otherwise. And this mode function is normalized, but it has no units. It's a unitless function, okay, because you have magnitude square of that thing from 0 to t is 1. So the electric field of an ideal laser-like pulse is going to be, uh, uh, so we are going to write it as E of t. So E of t will be the notation for an electric field as a function of time. And this electric field, I'm going to write it as the mode function times a complex number, A. And this complex number over here is A times e to the I theta. So that's the complex number I'm multiplying this mode function with. And there's this oscillatory part, e to the I 2 pi f naught of t, which is a constant frequency sinusoid that I'm multiplying the mode function with. So in the language of semi-classical optics, this is known as a quasi-monochromatic field. Quasi-monochromatic, why? Because I have, if I only had this e to the I 2 pi f naught of t, that would be a monochromatic field. It is an oscillatory function with precisely the frequency f naught. But if I take this e to the I 2 pi f naught of t and multiply that by pi of t, its Fourier transform will be the Fourier transform of phi of t, but shifted at f naught. So it will have a spread around f naught, but it will be a narrow spread if f naught is much larger than the bandwidth of phi of t. Okay, so if you take this electric field and take a magnitude squared of this whole oscillatory portion, this phase goes away. And if you take the integral of that from 0 to capital T, the integral magnitude squared of the phi of t portion goes away because that's 1, and you are left with a squared, right? Because this is the real number, so so you just get an a square over here. So this quantity, we are going to define the electric field in units of square root of photons per second, meaning that this magnitude square of the field integrated is going to give us the mean energy in the electric field in units of photons. Okay, so we are going to consider all of the electric fields or most of the electric fields in this course to be normalized in this following fashion, that if you take the magnitude squared and integrate that over the space and or time extent over which it has been defined, you're going to get the mean photon number in the pulse, or mean energy in units of photons. Okay, so this is where I've just sketched the field itself. So a over square root of t is the value, because phi of t is 1 over square root of t. So times a, so that's the amplitude. And this blue thing is the oscillatory portion that I'm just sketching over here. Now, all right, so the only thing that I needed to tell you to define the state of the field once I had identified the mode function phi of t is that complex number, right? So that complex number alpha, where alpha is 8 times e to the I theta, right? Because there was, if you forget about this oscillatory portion, which I'm going to assume that that all of the fields that we are going to talk about have the same oscillatory portion, the same center frequency. I'm going to drop that for most of the discussion. The only thing that really matters once we have identified the mode function is the complex amplitude, this a times e to the I theta. So that complex number we are going to denote as alpha. And for a semi-classical description of a pulse of ideal laser light, what you need to define is the mode in which you are exciting the field, and then that one complex number. Now, the quantum description of that same exact field, which will become clear in the next section that Prajit will talk about, is a coherent state of the mode phi of t. And the coherent state is the quantum description of an ideal laser light pulse. And we are going to write the coherent state as that same alpha, this complex number, enclosed in that ket. So every time we are writing a ket, we will have a mode in mind. So a coherent state of a mode is this alpha, is the complex number inside that ket, will define that coherent state of the mode. Now, for classical light, once you have identified a mode, I said that all you have to do is to give the complex amplitude, and you have the state of ideal laser light pulse. Now, if you're talking about a set of two orthogonal modes, the most general way for you to talk about an ideal laser light that is excited in the span of those two orthogonal modes is to supply two complex numbers, one for each one of those modes, okay, and so on. So let's take an example. So we'll take, say, two orthonormal modes, phi 1t and phi 2t, and I just define what orthonormal modes mean, meaning if I take phi 1 of t times phi 2 star of t dt, integrate that over their temporal extents over which they are defined, I'm going to get 0. And then let's consider a function phi of t, which is a superposition of these two mode functions. Superposition of the mode functions, meaning just sum of the mode functions multiplied by two coefficients c1 and c2. So c1 and c2 are two complex numbers. And let's assume that magnitude c1 squared plus magnitude c2 squared equal to 1. So now it is easy to see that this phi of t itself is a mode function. Okay, so how do you see that? Well, if you take the magnitude squared of phi of t and take the integral from, say, 0 to t over which, say, these two functions are defined, you take the magnitude squared of this and integrate it, you will get the first term will be the magnitude squared of phi 1 of t whole squared, which will become 1. So we'll get magnitude c1 squared will come out. And same with over here, magnitude c2 squared will come out. And there will be two cross terms. The cross terms will be phi 1 of t times phi 2 star t dt, which will be 0. And the other cross term will be phi 1 star t phi 2 t integral over dt, and that will also be 0. So, and then if this is true, then That's the only term that remains. So magnitude square of phi of t integrated over 0 to t will be 1. So which means that if you have two properly normalized mode functions, I can always construct another properly normalized mode functions by taking a superposition of those two mode functions such that this condition is satisfied for the coefficients. Okay, so now let's go ahead and consider a field E of t, a coherent state of the mode phi of t, this mode of phi of t that we just defined. And as I said, all we need to do is to supply this complex coefficient, as complex coefficient for the coherent state of this mode phi of t, which is a times e to the I theta. Now, if I take this and write it down, expand phi of t in terms of phi 1 and phi 2, I get this expression on the right-hand side. And now if you look at this expression, I'm going to again forget about this oscillatory portion. If you look at this, these two expressions, if I only had an electric field given by this portion of the expression, then it would be a coherent state of this mode phi 1 of t, whose complex amplitude is equal to a times c1 times e to the I theta. And if I again looked at, if I just had a field given by this portion of the expression, then it would be a coherent state of the mode phi 2 of t, whose complex amplitude is just given by a times c2 times e to the I theta. Now, the quantum description of this electric field is a coherent state of the mode phi of t, just like we talked about earlier, right? So I have excited phi of t in a coherent state alpha, which is equal to a to the I theta. The electric field is given by that, okay? But now that I have written this electric field in this new mode basis, phi 1t and phi 2 of t, I can re-express, I can just restate the quantum state of this electric field as the coherent state alpha 1 of this mode phi 1 and the coherent state alpha 2 of this mode phi 2. And this English word "and" that I just talked about, its mathematical ramification is something called a tensor product. So for those of you who have seen some quantum mechanics, you have seen this tensor product quite a lot. We're describing the state of the two quantum states that are of two independent quantum systems. So here I've written coherent state alpha 1, where alpha 1 equals to a c1 e to the I theta of this mode phi 1 and the coherent state alpha 2 of this mode phi 2. And for going forward, I'm going to drop this mode level over here, phi 1 and phi 2, but we will always remember that every time I'm writing a ket, every time you see a ket, a Dirac ket with something written inside it, that Dirac ket, you have to have a mode in mind or a collection of modes in mind. So in here, this ket refers to the state of the mode phi 1, and this ket refers to the state of mode phi 2. Another thing is that if in the same context, if you're writing two kets like this, tensor product of two kets, you have to be talking about two orthogonal modes. So this the mode for which you're writing this ket and the mode for which you're writing that ket are two orthogonal modes. So in this case, we know what the mode functions are. The most general way to describe the state of a field is to talk about the state of the collection of modes that the field has been expressed in. And this is a very, very important concept that underlies most of the things that we are going to talk about in this course, that in classical light, you first identify the set of orthonormal modes in which your field lives. And then you either supply the complex coefficients or complex amplitudes for all those orthogonal modes, in which case you will get a coherent state, a state of ideal laser light, or you supply with a probability distribution function of a set of complex amplitudes corresponding to those orthonormal modes, in which case the kind of light you're talking about is known as statistical light. So there is a whole field of statistical optics that talks about statistical light, where once you have identified the mode functions, instead of having the precise complex numbers for each one of them, you have like alpha 1, alpha 2, alpha 3, and so on. What you have is a P of alpha 1, comma, alpha 2, comma, alpha 3, and so on. So you have a probability distribution over those complex amplitudes, and these are called statistical light. We are not going to talk about statistical light, for example, thermal light in this course. But when you go to quantum optics, then there are more kinds of states of those modes that may exist besides coherent states. And you'll see that in the next part of the course. So when we do write a ket to describe a quantum state, again, we always have a mode or a collection of orthogonal modes in mind. And another important thing that is very critical to understand is that coherent state of a field is always single mode. So what do I mean by that? So let's take a little bit of a pause and ruminate over this and look at this expression for a second. So if I were to write down a field, okay, some E of t, and you have some temporal function, and you have an oscillatory portion, which I'm going to assume that it's the center frequency is fixed, so it's quasi-monochromatic, so I can take that out. I can always define a mode function that matches that temporal shape of the field, and I can normalize it. Okay, normalize it meaning I can define that mode function to match exactly the temporal fluctuation, temporal shape of the field, and multiply or divide by a constant such that magnitude squared of that function over that extent equal to integrates to 1. And then whatever is left over, whatever I had to multiply or divide by, that becomes the complex number that becomes the coherent state of that mode that we just defined. So a coherent state, meaning the state of a ideal laser light excited in any temporal spatial shape, is always single mode. But then I can rewrite or re-express that coherent state in another set of orthonormal mode bases that span the same temporal extent, the temporal extent that the field spans. And now what you will have in that new mode basis is a tensor product of coherent states, alpha 1, alpha 2, alpha 3, and so on. So this concept generalizes obviously to beyond two modes. So coherent state, when expressed in any orthonormal mode basis, say phi 1, phi 2, say phi n of t, is a product state of the form alpha 1, coherent state alpha 1 of phi 1, and coherent state alpha 2 of phi 2, and so on, coherent state alpha n of phi n. And re-expressing this coherent state in a new basis is mathematically equivalent to a unitary transformation, a unitary operation. Now, I'm going to assume that you have seen unitary matrices in some form, your linear algebra. A unitary matrix U, a complex valued unitary matrix, satisfies U Hermitian conjugate, or U dagger times U is identity. And if I take these coherent states alpha 1, alpha 2 to alpha n, if I were to take these complex coefficients and multiply that by a unitary matrix, we get another set of complex coefficients. This transformation going from the alpha vector to the beta vector is the mathematical operation underlying expressing the electric field that we are talking about here with these coherent states of these modes in another modal basis. Okay, so what I mean by that is if I were to write down the field description of what I have written over here, this is E of t is summation of alpha I times phi I of t. Right? And what I'm doing now is that, so I goes from 1 to n. And I want to re-express the same electric field in terms of another basis, psi I of t, where psi I of t's are also mutually orthogonal amongst themselves, but they span the same linear algebraic span of these mode functions phi I of t. Then going from alpha I vector to the beta I vector is this unitary transformation, this unitary matrix. Okay, so this why does it have to be unitary? So so first of all, it's very easy to see that if I start with any set of values alpha i's, that there must exist a unitary such that you can collect all the amplitudes into a single one at the output and have the other ones be 0. It is very easy to see that. And this is another way you can see why a coherent state is always single mode, meaning I can always find a modal basis such that all my coefficients are collected in terms of only one function, and the rest of the functions, the coefficients are zero, meaning those are excited in vacuum state. Now, the fact that this is unitary ensures that the sum of the magnitude squared of the alpha I is equal to the sum of the magnitude squares of the beta i's. And physically, this corresponds to photon number preservation, meaning the mean energy in the input field is same with the mean energy of that same field written in another basis. So I'm writing the same field, but in two different bases. Now, example of this change of basis from the previous slide can be seen now as a unitary transformation. So remember in the previous slide, we said I'm going to take a coherent state alpha of that mode phi of t, and then I wrote phi of t as a C1 phi 1t plus C2 phi 2t. But now what we can do is that we can take phi 1 phi 2, and I can introduce another function phi vac of t such that the linear algebraic span of phi 1 phi 2 is same as the linear algebraic span of phi t and phi vac t. By the way, I'm using liberally concepts from linear algebra, like the word span, and I'm assuming that you know what a span is. A span of two vectors is the set of all vectors that can be written as a superposition of those two vectors. And same is true for functions in this case. Okay, so once I define this phi vac of t, now you can reinterpret this change of basis as a unitary transformation that I used to going from the mode basis phi t phi vac of t to the mode basis phi 1 of t phi 2 of t. And I've just re-expressed that field in this new basis. Now, this particular tube input unitary transformation is known as the beam splitter unitary, and we are going to talk next a little bit more in detail about this beam splitter unitary. But before we do that, let's do a few exercises of changing the mode basis, because we have been talking a lot about of re-expressing the coherent state in different mode bases. So before we go forward, let's do some exercises. So just for continuity's sake, I'm going to take the same exact mode function that we took for the first exercise. Okay, so this is your the phi of t, and for ease of working out this problem, I'm going to let you know also the value of a. The value of a such that phi t is properly normalized. Now, here I have defined the pixel basis. So pixel basis are those mutually non-overlapping orthonormal modes that we talked about a few slides back. Now, just for your completeness, this value is t by 4. This value over here is 2t by 4. This is 3t by 4. And this is capital T. Yes. And phi 1 of t, the value is square root of 4 by t. Why? Because the magnitude squared of phi 1 of t, it has to integrate to 1 and so on. So what I'd like you to do is to represent the coherent state alpha of this mode phi 1 of t. So alpha of phi of t, I want you to re-express this in the pixel basis, meaning I want you to write down this as a coherent state of phi 1 of t and a coherent state of phi 2 of t and a coherent state of phi 3 of t and a coherent state of phi 4 of t. And I would like you to find out the coefficients that correctly describe this electric field in this pixel basis. So go ahead and give it a try. I'll wait for about a minute and then we'll go from there. I would again really strongly urge for people to try to work this out. And I would love to see the participation percent go above 50% at least before I move forward. Okay, so I see 35% participated. While you're working on this, uh, before you do the math, you should also try to intuitively look at the pixel modes and see what sort of an answer you should expect to see, right? So if I were to re-express this function as a scaled sum of these four functions, I'm going to have the two same values over here and here, and two same values over here and here. And the two same values over here and here are going to be larger than the two same values over here and here. So that's the first thing. And then the rest is just working out the math just between one or two of these differing segments to see if you get the right ratio of these two amplitudes. Okay, let's go ahead and end the poll, Brianna. So we have almost 50%. And the the correct answer is B. We have the most people have picked B, but C is pretty close. Uh, I think it's just a matter of working on normalizations correctly. So the main hint is that what I just said is that write down phi of t in terms of the constituent mode function. So if you see over here, what I did is I took phi1 of t. Okay, so take phi1 of t, this function, and multiply that by square root of t by 4. If I multiply this by square root of t by 4, I'll get 1, right? And then once I get 1, I can multiply by a to get this portion of phi of t, right? So from 0 to t by 4. Then I can safely add the phi2 component because phi1 is 0 after this. So again, I take phi2, okay, and I multiply that by, again, square root of t by 4 to get 1 here. And then take that 1 and multiply by 3a by 2, because a plus a by 2, the height of phi t is 3a by 2. Who again gets this portion. So that's 3a by 2 times phi2 of t, and so on. And now once I've written it like this, then look at phi1 of t portion, and then phi of t equals to this. So your a value is of square root of 8 over 13t. You can substitute a. The square root of t cancels out, and you will get these coefficients, square root of 2 by 13 square 9 by 26, and so on. Pretty straightforward. Like this was just eyeballing. I'm just writing phi of t in terms of these pixel modes. And then after that, you go ahead and substitute and work it out. Okay, let's do another example. And this one will be a slightly more complicated. But I would, again, really like you to try to work this out, because to understand the concept of orthogonal modes, changing mode bases, these are good practice problems. So remember, we talked about when we were discussing the time frequency bandwidth or time frequency product, we talked about the pixel modes, and we also talked about these Walsh-Hadamard modes. So I have here sketched out the four mutually orthogonal Walsh-Hadamard modes between 0 to capital T. And this is the same phi t as in the previous slide. You can use the a value that I showed previously. And now I would like you to represent a coherent state alpha of this mode phi of t in this Walsh-Hadamard basis. So go ahead and start the poll, Brianna. And this time I'm going to let you work on this for a few minutes. So just try to see if there are multiple ways to work on it. There's some answers you might be able to rule out, and then but you can work it out from first principles. So again, you have to write down this function phi of t um, times alpha, which is the electric field excited, a coherent state excited in this mode phi of t, or a coherent state of this mode phi of t, and re-express that as a coherent state of this mode psi1 t, and a coherent state of this mode psi2 t, and a coherent state of this mode psi3 t, and so on. And I want you to write down those complex coefficients for these modes psi1, psi2, psi3, psi4. All right, I think we should go ahead and close the poll. We clearly are seeing a winner emerge here on number C, and the right answer is C. So very, very good job on finding this out. Um, so I wonder how people arrived at the solution. What I would have done if you were looking at staring at these four options as the only possible options is just to look at the intuitive way out. So if you look at this function, I am saying that there is no component of psi 2 and psi 3. So you're basically adding something times this function and something times this function to get this shape. Like if I take positive coefficients for this and this, right, I'm going to get a bigger value over here and a smaller value here because this is negative. So I'm not going to get a shape like this. I'm going to get a shape that looks more uh, like this, right? So this one is ruled out. And similarly, you can rule out this one and this one. And this is the only one that's going to give you a shape that looks like this, because in the middle portion, I'll subtract a negative value over here. So I'm going to get a shape like this. Anyway, but if you wanted to do it properly, then one easy way to do it would be to use the inverse transformation, meaning if you take phi 1 of t, and phi 2t, phi 3t, phi 3t, the mode functions that we talked about in the previous slide, the pixel modes, we can re-express those pixel modes in terms of the Hadamard modes, in terms of these Walsh-Hadamard modes, right? And why can you do that? So the same way so we said that the psi modes can be written in terms of the phi modes. It means that the phi modes can be written in terms of the psi modes and with a dagger. And for the Hadamard matrix, U and U dagger are the same. So this is the relationship of the pixel modes expressed in terms of the Hadamard modes. Okay, and then once you have that, then you take phi of t, which is this function. And we had already written this in terms of the pixel modes, the previous problem. Now, each one of these pixel modes has been re-expressed in terms of the Hadamard modes. So I can go ahead and substitute phi 1 of t from here, phi 2 of t from here, and so on, and then work it out, and I'll get these two coefficients. So if we did not have these options here, then you would have to work it this way and get this answer. But excellent job. Okay, so let's move forward. The next concept we will talk about is mode sorting. Okay, so before this, we have talked about modes, we have talked about orthogonal modes, we have talked about unitary transformations of modes, meaning re-expressing the coherent state of a field in different set of orthonormal mode bases that span the same linear algebraic span of mode functions. But now we are going to talk about separating a set of modes. Remember, we talked about this example of CDMA phone standards, mobile standards using the Walsh-Hadamard modes as a chip sequence to simultaneously send information about multiple callers. So if these are the Hadamard modes, this E in of t, this function that I'm writing here, the A1, A2, A3, and A4, they could be signals that are being modulated or put into these four orthonormal functions. They live in the same time span from four different users, and you're propagating them together. So E in of t is the field that is being sent. But when a set of mode functions are orthogonal, it means that you can separate out the content in these modes, meaning I can always go from any set of orthonormal mode functions to a time separated set of orthonormal modes, which we defined as the pixel modes, meaning there always will exist a device, which I'm just here calling a mode sorter, where if I were to put in this field En of t, then on the output, I'll get E out of t, which will be the exact same coefficients A1, A2, A3, A4, but on the pixel modes instead of them multiplying these time overlapping orthonormal modes. Why do we call it mode sorting? Well, if I wanted to detect light in these modes individually. If I wanted to detect this mode and this mode and this mode and this mode separately, here they're all jumbled up. They're all occupying the same time span. Once I have done this transformation, then I can detect light from 0 to say t by 4, and only A1 is going to drive my photon arrival rate. And again, from t by 4 to t by 2, only A2, that amplitude of this phi 2, is going to drive my photon arrival rate, and so on. So transforming a set of time overlapping orthogonal modes to a set of time non-overlapping pixel modes is the act of mode sorting. Now, there are multiple hardwares that can do this mode sorting. For example, for polarization mode sorting, something called a polarizing beam splitter does the job. For spatial temporal mode sorting, there are all sorts of different ways in which you can sort modes. And this is, by the way, an area of active research. There's one kind of mode sorting that I'm going to talk about very briefly without going into proofs. It's called multi-plane light conversion. This works both in space and time, meaning for sorting orthogonal spatial modes versus orthogonal temporal modes. So let's talk about the multiplane light conversion in the context of spatial modes. So far we have been only talking about temporal modes, but we'll talk about MPLC, multiplane light conversion in the context of spatial modes, because that's what has been physically realized in a laboratory setup that I want to briefly talk about as well. So let's take a coherent state pulse, phi 0 of xy, that I have represented in a spatial orthonormal basis. So so there is no phi 0 of xy. So I'm sorry. So this should have been E 0 of xy. Okay, so coherent state E 0 of xy. I'm writing that in this modal basis. Okay, so this should be this is a typo. This is E 0 of xy. So these A and M's are the complex amplitude. So it's a coherent state A00 of the mode psi 00 and so on. And these mode functions are orthogonal. Now, let's take this coherent state E0 of xy, and we'll multiply this with a spatially varying phase theta of x comma y. Okay, so this multiplication of a field by a phase can be done by a physical device known as a spatial light modulator. You can take a spatially varying field and you can pass it through a gadget that you can electronically program to apply different phases at different spatial locations. And then I'll get a field that I will call E1 of x comma y. And then we will express E1 of x comma y in the same model basis that we had originally expressed E0 of x comma y. And this time we'll get different coefficients. And so here I see another typo. I'm sorry about all these lingering typos over here. So there's a summation missing here, n comma m. Okay, so E1 of x comma y, I'm just representing in the same modal basis. So what I want you to do is to express this coefficients b and m's in terms of the coefficients a and m. So it's not an exercise, but we'll work on it together. So how do we do that? Well, so we'll take the expression over here for E0 of x comma y, which is over here, E0 of x comma y. And I multiply this by e to the I theta of x comma y, right? So this expression is the expression for E1, because this is E0 times e to the I theta of x comma y. And then the right-hand side is just, I reproduce, because I want to write E1 in terms of the mode function psi n of x comma y. So the right-hand side is the same as above. The left-hand side is, I've just rewritten E0 in terms of the A's and multiplied e to the I theta x comma y. And this is just the pictorial denoting multiplying E0 by a spatially varying phase. So this is what a SLM, a spatial light modulator, is. And theta, this theta vector is the set of thetas that are being applied on all these little pixel modes, x comma y. Okay, so now how do you get B's in terms of the A? So it's a standard linear algebra trick. If you have done mode basis conversion problems in linear algebra, you would have done it many times. So you take the left-hand side and the right-hand side, and you're going to multiply both sides by psi kl x comma y complex conjugate. So see, all the black font is exactly the same as above. The red font is what I'm multiplying on both sides. And then after that multiplication, I'm integrating both sides. That's the blue font. Okay, so once I do the integration, on the right-hand side, what happens is that this portion, this integral come inside. And when the two integrals come inside, these functions are orthonormal. So what you get is a delta function at nk and ml. So the only term that survives in this summation is when n equal to k and m equal to l. So bkl is the only term that survives. And on the left-hand side, what you see is that if you take this whole thing, put it in a square bracket, and give it a name unm comma kl, then what you can see is that to go from the A coefficients to the B coefficients, it's just a matrix multiplication. So the B equal to some unitary matrix times the A matrix. And this multiplication by this particular spatial phase is nothing but a mode transformation. So we have transformed the mode from the coefficients from A to B, where the unitary transformation, it depends upon the spatial phase that we have applied. Okay, let me erase my annotations from the previous slide. And Prijit, if you could please make note of all these typos so that we can fix the slides and we'll send out the PDF. Okay, so now let's just recall from the previous slide. If E1 is E0 times this spatially varying phase, and now we are going to take this E1 field and we are going to pass it through a 4F system. A 4F system in optics is a transformation through two lenses that are separated by twice their focal lengths, and it's a Fourier transform, meaning E1 of x comma y through a 4F system. It's just a optical propagation. Does a Fourier transform for free. You get an E2 of at another spatial coordinate x prime y prime, which is a Fourier transform of E1. And I want to now rewrite E2 of x comma y, x prime comma y prime after this Fourier transform in that same modal basis. And I get another set of coefficients C's. And this is just the expression for the Fourier transform. So going from E1 to E2, this is what a 4F system does. And now I want to see that going from the B coefficients, meaning if B coefficients were expressing E1 in this modal basis, to the C coefficients, which is expressing E2 in that same modal basis, that also is a unitary transformation. I'm not writing out the full equation. You can work it out using this exact same method that I used in the previous slide, except by expressing both sides in their respective coefficients and then multiplying by the complex conjugate of an arbitrary mode function from that set and taking an integral. You're going to get C equals to some fixed unitary V times B. And an MPLC or a multiplane light conversion, the idea is that you keep repeating it many times. So you take the initial field, I'm expressing it in this some modal basis. So these are my initial coefficients. And I first multiplied by a spatially varying phase θ1, then propagate it through a Fourier transform distance. This is the Fourier transform. Again, have a spatial light modulator that multiplies the field by another spatially varying phase, another Fourier transform, and so on. So what happens is that your coefficient AN gets multiplied by a U θ1 and then a fixed Fourier unitary V, then U θ2 and a fixed unitary V, and keep going. And what you can prove is that so this overall unitary U that you have realized by this many times propagating through this successive Fourier transform segments and spatial light modulators can approximate any unitary as closely as you wish if you have a sufficient number of these SLM stages. So this is known as multiplane light conversion, and which means that I can realize any U and any unitary transformation. So this method has been used in the laboratory to separate spatially overlapping orthogonal modes into spatially non-overlapping pixel modes because they are both unitary mode sets or orthogonal mode sets that span the same linear algebraic span. So we talked about the Hadamard modes in time. So you can define the Hadamard modes in space, exact same way. So Hadamard modes in space in x and y coordinates are just the product of the Hadamard mode functions in the x variable and the y variable. So here, for example, I have sketched out the Hadamard mode functions for a k equals to 4. So these four spatial modes, meaning a spatial mode that is zero phase over this spatial region, zero phase over here, and pi phase here, and so on. These four are orthogonal spatial modes. I think if I take any two of these, multiply, integrate over that spatial region, I'll get 0. This is the picture of a multiplane light conversion device that was built in my lab by my students Michael Grace and Itai Ozer. And what you're seeing here is this is a little spatial light modulator. And what we are doing is that in the first bounce of the spatial light modulator, we are encoding one of these four Hadamard coded modes of phase patterns 0 and pi in those four patterns that I showed in the previous slide. And then there are 3 segments of that SLM that we are using for 3 bounces interspersed by Fourier transforms between them. So it's an MPLC with 3 bounces. So capital N equal to 3, meaning 3 bounces that we are going through. And we have coded up these SLM phases, the theta 1, theta 2, theta 3, those spatially varying phases, such that after that propagation, if you had sent the first Hadamard coded mode, you will see a spot of light in one location, meaning you will sort it to 1 pixel mode, and so on. So here, for example, we are showing the sorting of 2 orthogonal modes. So this is an orthogonal mode. So this is 0 phase, this is pi phase, this is 0 phase and pi phase. So these 2 modes are orthogonal. And depending upon which mode pattern goes through these 3 spatially varying phases, meaning, so this is theta 1, theta 2, and theta 3. So this comes from an algorithm. Depending upon which one of these 3 goes, you will get a spot of light over here or a spot of light over here. So now you can see that this is these 2 are pixel modes. I have defined spatially separated regions. So this is a pixel mode. This is 1 pixel mode. And over here, I have defined another pixel mode on the top left corner. And depending upon which one of these 2 mode patterns go, you get a spot of light in the first pixel mode or the second pixel mode. And now the light falls into a camera. This is the camera, and then depending upon where you see the spot of light, you'll see those pixels light up. So you can separate these spatially overlapping modes into spatially non-overlapping modes. So this is mode sorting. And similarly, you can sort these 2 mutually orthogonal modes into 2 different pixel modes in the output. So let's do a very, very simple, almost like a thought exercise. So I'm not going to spend too much time on this, but let's first look at the setup, because it's more important to understand the setup, and the problem will be very easy to see once you look at this. So you have these 4 Hadamard, orthogonal Hadamard spatial modes. Okay, so Walsh-Hadamard modes. And we have built an MPLC, a multiplane light conversion device, which, if presented with this red mode, you will see a spot of light in this region. So these 4 are the pixel modes. So if I only excite the field in this mode, I'll see only a spot of light in this mode. If I only excite the field in this mode, meaning if I have a coherent state of this mode, I will only see a spot of light in this mode, and so on. Okay, so the blue will go to blue and the orange will go to orange. But if I write down a field that is C1 times this plus C2 times this, then I will get a light in the red bin and the gray bin. And depending upon how big C1 and C2 are, you will have a brighter and a dimmer spot of light in those 2 modes, because we are just sorting, we are transforming these modes one by one to those pixel modes. So my question is that we have presented the MPLC with two fields in two separate experiments. Okay, so this is the first one, the first field, and this is the second field. And for each one of them, I have gotten, and this is actually, by the way, the real camera record from the experiment. And I have shown the camera record from the experiment, the light that you see on the EMCCD camera. So what I'm asking you is that which corresponds to which? Meaning option A is that when I present the MPLC with this field, that I see spots of light in these two pixel modes. And option B is that when I present this field to my MPLC and the output on the camera, I see a spot of light in these two pixel modes and vice versa. So why don't you try, take a few seconds and see if you can figure out which of these two answers are correct. And again, there's no math here. It's just intuition. So you should be able to really look at the phase patterns and work it out. All you have to see is that see if you can express this as a linear combination of some set of modes and make sense of the output. And by the way, these colors simply denote the phase value on a color scale that I've denoted here. So I see more than 50% participation already, so we can go ahead and close the poll. So the correct answer is indeed A, which more people have voted for. And it's simple to see that you can get this field pattern by adding up contribution from the first mode and the last one, this mode over here. That's the only way you can get these two colors to be equal and these two colors to be equal. And this field pattern you can get by adding the second mode and this third mode. And see if you add this over here, this blue and this blue, you get dark blue. This is, again, I'm not showing real values, but just to get a feel for the phase values being different over here and the field phase values over here being same and so on. So so clearly you have the contribution from gray and the cyan for this one, and that's why you should see light in the gray bin and the cyan bin. Okay, so this multiplane light conversion has found many uses. So one of the most recent investigated uses of a spatial mode sorter has been in the context of super resolution imaging. I won't have time to go into this in detail, but this is a cartoon picture from a simulated experiment that we have just finished a real experiment of, and it's in reviews right now. What you're seeing here is the field of view of an image where you have three spots of light. So for example, from a telescope, you're looking at three stars. Okay, so this black dots are where three stars live. And the field of view is extremely tight, extremely small. Extremely small meaning the angular extent of this field of view is much smaller than lambda over d, where lambda is the wavelength of light and d is the diameter of the entrance pupil of your telescope, which is known as the Rayleigh limit. So when two stars come much closer than the Rayleigh limit, a focal plane camera, a normal imaging system cannot resolve it. But in this case, what we are doing is that after the light is collected by the telescope, instead of imaging it on a camera directly, imaging it on the CCD array, sensor array directly, we are passing it through a mode sorter. And not only are we passing it through a mode sorter, this mode sorter is a adaptive one, meaning we are sorting these set of modes, phi 1 through phi k. We are detecting photons in them and then processing the results to immediately decide what next mode basis to sort the next incoming chunk of light in, and then reprogramming the SLMs to sort those new set of modes. And we are continually doing that through the whole integration time. And as you are integrating more and more photons, so 30,000, 60,000, 90,000 photons, a normal telescope, which is direct imaging, it is generating an estimate that there's only one bright star sitting at the average location of where the true star locations are. But then the modal imaging method can localize where the true stars are, even though the separation between them is highly subrelay. So this is a very interesting area of exploration that has applications in fluorescence microscopy, to astronomy, to space domain awareness, and many other applications. Similarly, another whole new area of application of mode sorter has to do with shaping quantum states of light. So in this course, we will not talk about any other quantum state of light other than coherent states and number states, which Prajit will discuss. But there is a very interesting state of light known as squeeze states of light. And so you can prepare squeeze states of light or generate them using a nonlinear crystal pumped with a laser light. And if you take a squeezed light source and you put it through a mode sorter, what you get on the other side is an entangled state of light across a set of co-propagating orthogonal spatial modes. An entangled state of light means that you cannot talk about the states of those modes individually. You can't write down the state of the first mode and the state of the second orthonormal mode and the state of the third orthonormal mode. You have to write down the joint state of those collection of modes. It doesn't factor. And this particular case, this particular entangled state has found applications in high resolution or high precision sensing of beam deflections, and has applications in atomic force microscopy, pointing acquisition tracking for laser communications, and so on. Exact same mode sorting, spatial mode sorting, has found also commercial uses in laser communications on multimode optical fiber. I'm sure you have heard about wavelength division multiplexing, time division multiplexing. We already talked about code division multiple access, where you take these Hadamard Walsh coded temporal modes and send multiple user signal on together. There is another form of multiplexing, meaning sending multiple signals on one fiber, that is spatial mode multiplexing. So if you have a thick enough optical fiber that can accommodate multiple co-propagating orthogonal spatial modes of light, then you can, if you have a mode sorter like this, you can demultiplex and multiplex multiple signals on orthogonal spatial modes and propagate that along that optical fiber. There is a company called Lab based in France that commercially make mode sorters that are designed particularly for this purpose. Okay, so now let us talk about detection of a coherent state of a mode. So these are the pixel modes that we talked about earlier. And this is the coherent state of that flat top mode. So alpha is the complex amplitude. And I'm going to take alpha to be real, to be for ease of it. So alpha is square root of n. N is the mean photon number. And the mean photon number is the squared of the field integrated over the duration, as we talked about. So it is E squared times t. So that's your mean photon number. And this is the mode function phi t. So this is a coherent state alpha of that mode phi t. Now, I can rewrite this coherent state of this mode phi t as a coherent state gamma of this mode phi psi 1t, and a coherent state gamma of this mode psi 2t, and a coherent state gamma of this mode psi 3t, and so on. So gamma is the same for all of these. The gamma is square root of n over m. Why? Because the mean photon number of this coherent state, gamma squared, is n over m. So the mean photon number added over all of these modes is n. So I'm just re-expressing my initial, my field, which is coherent state alpha of this mode phi t, in terms of the coherent states of these modes. And you can derive this very easily. Just write down this field E of t, and you can write this as a psi1t times a constant plus psi2t times a constant plus psi3 times a constant. The constants will all come out to be same, and they're all gamma. And then I'm going to take M to be very large, where M is the number of these pixel modes I have defined in that fixed interval capital T. So as I take M to be larger and larger, I must choose a tau, the mode extent, to be smaller and smaller. So I'll take M to be much larger than 1. Now recall that if I were to take a coherent state alpha and then we are going to detect photons. Okay, so I should say have said recall because this is the first time I'm telling you about this. So if you were to detect photons on a coherent state alpha, what you get is a Poisson distributed photon clicks, meaning you will get k photon clicks, where k is a random draw from a probability distribution given by e to the minus capital N, n to the k over k factorial, where n is the mean photon number of this coherent state. Okay, so when n is small, then what happens is that it's just the first term and the second term that matter, because these terms P2, P3, P4, they become smaller and smaller very rapidly. So probability of detecting k photons on a coherent state gamma, this little coherent state gamma on this mode psi I of t, is given by the same expression like that I've written here, except that n has been replaced by n by m. So if you look at this expression, because when m is very large, n by m will be very small, and when n by m is very small, only the first term and the second term matter, as we just said. So meaning that if I were to detect photons on this little coherent state of that mode psi1 of t, I'll either get no clicks with probability e to the minus n over m, or I will get one click with probability 1 minus e to the minus n over m. Again, this is a typo. This is not an equal sign. This is a minus sign here. Okay, so then if we already mentioned that the coherent state description in these modes psi1, psi2, psi3 is a tensor product, meaning it's a coherent state of psi1 and a coherent state of psi2 and a coherent state of psi3 and so on, which means that as I detect photons on this mode and this mode and this mode and so on, the statistical process of the clicks arriving or not in each one of those modes, psi1, psi2, psi3, psi4, are statistically independent. Okay, so the rate at which photons are arriving are the mean energy, mean photon number of this coherent state divided by the time extent. So it's gamma square over the time extent is tau. And gamma square over tau is n over m tau from this expression. And m tau is capital T, which is n over t, which is equal to e squared. So this e squared, which was the magnitude squared of the field in photons, root photons per second units, is photons per second, and that's your arrival rate of the of the photons when you detect photons on a coherent state. Which means that if I were to take this pulse of light, meaning this field that is a coherent state alpha of that flat top mode, and feed it into a detector, what I will see is known as a Poisson point process. It's a memoryless arrival process, meaning in every little time chunk that goes into the detector, I will have an independent probability of a photon arriving or not in that little time segment. And the photon arrival statistics for every subsequent little time chunk will be statistically independent of the photon's arrival or not in the previous time segment. There's a whole literature on Poisson point processes, which again, I won't have time to go into, but this is a very simple, intuitive way to understand why the photon arrival process on a coherent state is a memoryless Poisson point process. So hold on to that thought. And another thing that we are going to need for some of the application section of this course is what happens if I take two coherent states and interfere them on something that is known as a beam splitter. I had introduced the word beam splitter when we talked about a two-mode unitary transformation earlier in the course. Okay, so this is how we are going to denote a beam splitter. A beam splitter is a device, if you want to see a beam splitter in the lab, a physical or bulk beam splitter, it looks like a cube of glass. It's a piece of glass. And you put you light into two facets, two inputs, and you see light coming out on the two outputs. So the beam splitter is defined by two things. It's a transmissivity eta and a phase that I'm writing here as a theta 2. So eta is the transmissivity. The transmissivity tells you what fraction of the input amplitude goes into the corresponding output amplitude. So alpha 1 and alpha 2 are the input amplitudes of two coherent states I'm feeding on the beam splitter, and beta 1 and beta 2 are the two amplitudes of coherent states that come out on the output of the beam splitter. This is an interesting property of coherent states, that if I were to feed in two independent coherent states at the input of a beam splitter, the output is also a tensor product of two coherent states, meaning I get a coherent state on the first output and a coherent state on the second output. The coefficients, the complex coefficients, so the field amplitudes of those coherent states, beta 1 and beta 2, are expressible in terms of the coefficients of the input coherent states, the complex amplitude of the input coherent states, in terms of a 2x2 unitary transformation. So this is the most general unitary 2x2 unitary transformation. Eta is the transmissivity and theta 2 is the phase. Sometimes you would see eta, the transmissivity, also written as a phase by expressing eta as cos square of theta 1. So theta 1 was a one phase between 0 and pi, and theta 2 is another phase between 0 and 2 pi. So it's the most general unitary. So let's work out a couple of examples. If I take this unitary over here, and I set eta to be 1/2 and the phase of the beam splitter theta 2 to be 0, and if I put in alpha here and minus alpha here, I'm going to get, so the first output beta 1 is alpha 1 plus alpha 2 divided by root 2. Okay, so alpha plus minus alpha over root 2, which is 0. And the second output will be alpha 1 minus alpha 2 over root 2, which is square root of 2 alpha. So this is where you can see constructive versus destructive interference. So all the energy at the input, so alpha square is the mean photon number here, and alpha square is the mean photon number here, and 0 is the mean photon number here, and square of this, which is 2 alpha square, is the mean photon number here. So the photons from both the inputs collected themselves as at one of the two outputs. So there's and this is the kind of interference that you see also when you have ripples of water in the lake interfere with each other. It's the exact same. This is the classical interference that you see when you mix coherent states in a beam splitter. We'll also hear about quantum interference when you mix non-classical states of light on a beam splitter, which does not have a classical analog. Another simple example is that I'll set eta to be 0. If I set eta to be 0, it becomes a pure reflection or pure transmission. You're just sending alpha to one port and sending beta to the other, and you can have a non-trivial phase, which is not 0. So beta gets multiplied by a phase. So this we are going to call a application of a phase to a coherent state. So I'll write it compactly like this. So beta goes through a phase, theta 2, to get beta times e to the theta 2. Physically, this phase can be realized by a phase plate, or applying a localized heat, or an electro-optical voltage to in a photonic integrated waveguide to apply this programmable phase. Another interesting use of a beam splitter is to do a phase space displacement. So what I mean by that is, if I now, let's take alpha and gamma as the two inputs, and I set eta to be 1 or close to 1, meaning maybe eta is 0.9999, set theta 2 to be equal to 0, and pick gamma to be a large coherent state. So take gamma to be some beta divided by square root of 1 minus eta. So beta is a fixed number, and I'm dividing that by square root of 1 minus a number that is very close to 1. So this number denominator is very large. So that's why gamma is very big. So now if you look at the first output, what you will get over here is square root of eta alpha. So I'm just looking here, square root of eta times alpha plus square root of 1 minus eta times gamma. But gamma is beta over square root of 1 minus eta. I've chosen gamma to be that. So this cancels out. And eta is very close to 1, so I can ignore this also. So this output is roughly equal to alpha plus beta. And this is very interesting because this is something that you can use to apply a displacement in the in the complex space. So if I give you alpha, a coherent state alpha, and if you want to add some other complex number beta to it, this is the circuit you can use with a single beam splitter to apply that displacement. The Mach-Zehnder interferometer is a name given to this particular setup that is built with two beam splitters. Both beam splitters have equal transmissivity equal to 1/2, and phases θ2 and 2 θ1 in the, like I've shown here. If you work out the math from the input to the output, meaning take this alpha1, make it go through θ2, so you'll get a coherent state alpha1 e to the I θ2 here, alpha2 comes here, and you apply the beam splitter, you write down the coherent states and keep following. You will get this 2x2 unitary transformation. So that's the most general 2x2 unitary transformation can be realized by two 50-50 beam splitters and two variable phases. And in general, if I were to write down this one MZI as this U of θ1 comma θ2, so if I write it like this little cross here, then if I wanted to realize an arbitrary n input, n output unitary transformation, which I had shown you a few slides earlier, there is a beautiful theory that we can read about from this paper from Reconciling in 2094, and then a more modern version from this 2016 paper, that you can write down this n by n unitary break it up into n times n minus 1 over 2 times MZIs. Now, each MZI has two fixed transmissivity beam splitters and two variable phases. So two variable phases per MZI, meaning I need n times n minus 1 divided by 2 times 2 number of variable phases. So n times n minus 1 by 2 variable phases to realize a general n by n unitary. So there are lots of people in the community, including Professor Dirk England, who is Deputy Director of the Center for Quantum Networks. He's a professor in MIT, done a lot of very interesting work in photonic integrated circuits and applications. His group realizes these photonic integrated circuits on chip, where you basically go ahead and you apply these n times n minus 1 number of tunable phases by a set of directed applications of heat on a nanophotonic array of 50-50 beam splitters. And when you apply heat to a location, it changes the refractive index of light locally, and that changes the path length locally by a tiny bit that applies that phase. So you can program a linear optical unitary circuit by tuning those phases. So with that, let's do one exercise which will use both of the things that we just learned. Okay, so we learned two important concepts. One was detecting photons on a coherent state, where we learned that if I feed a coherent state into a detector, you get a Poisson distributed random variable whose mean is equal to the mod squared of the coherent state amplitude. That was the first concept. Second concept we learned was what happens when you interfere two coherent states in a beam splitter. So this problem is going to use both of those two concepts. So consider a 50-50 beam splitter where I interfere alpha and beta, the two coherent states, on a beam splitter of transmissivity 1/2. So you get alpha plus beta by √2 and alpha minus beta by √2 and two outputs. And so this is the convention we are going to use. Okay, so this 50-50 beam splitter. So now let's consider this particular setup. So this setup, I have two 50-50 beam splitters and two phases, one phase here, one phase here. So this kind of looks like the Mach-Zehnder interferometer, but not quite. It's a different setup. Okay, so I have one phase here and one phase here. This phase is fixed. This θ2 is 0 always. I'm still writing it as a box, but θ2 is 0. θ1, I go ahead and I can turn θ1 to 0 or to pi without telling you. Okay, so I can set θ1 to be 0 or θ1 to be pi. And your job is to identify which is the phase θ1, either 0 or pi. And so you're discriminating between either 0, 0 or pi 0. So there are two phase patterns, either 0, 0 or pi 0. Your job is to tell them apart. And you are presented with a coherent state probe. So this coherent state alpha is the laser that you're shining. And what happens to the output of the first beam splitter is you get an alpha by √2 and alpha by √2. Why? Because you get an alpha plus 0 by √2 in the top port and alpha minus 0 by √2 in the bottom port. Now alpha by root 2 multiplies this phase. So phase is 0 or pi. If it is 0, you get alpha by root 2. If it is pi, you get minus alpha by root 2, right? And if it theta 2 equal to 0, this alpha by root 2 comes out here. Okay, so now this beam splitter, I'll let you work it out. Okay, so if theta 1 is 0, this plus alpha by root 2, you can work out the output here. And if it is pi, you can work out the output here. And then these two detectors are ideal detectors. And just look at if the detector clicks or not. So if your coherent state alpha falls into a detector, you will get 0 clicks with probability e to the minus alpha squared or mod alpha squared. And you'll get more than 0 clicks with probability 1 minus that. So work out the click, no click probability and use that information to make a guess about whether you had seen 0, 0 or pi 0. And tell me what is the probability of making an error for choosing the right pattern. If the prior probability of both of those patterns were equal to 1/2. So I'm obviously assuming that you have some background to in Bayesian probability theory. So see if you can spend a few minutes. So this involves 3 different concepts that we learn. So it's a slightly more involved problem, but I'll walk you through the solution. But you should have all the information from what we had just discussed. So as you're starting to work on this problem, I'm going to show you one picture here on the right hand side, just so that you have a little bit easier job at solving this problem. So when theta 1 is 0, you have this situation, right? You're putting in alpha by root 2 and alpha by root 2 through the second beam splitter. So you get an alpha here and a 0 here. When theta 1 is pi, you're putting minus alpha by root 2 over here. So you have this situation. You get this plus this over root 2. So you get 0. And this minus this, you get minus alpha here. Now, when alpha goes into this detector, you get a probability of no click is e to the minus n, where n is magnitude alpha squared. And you get a probability of click is 1 minus e to the minus n. Whereas this other detector, it it never generates a click because you're feeding 0. So probability of click is 0. Probability of no click is 1. But the exact opposite happens if it was the other phase pattern. So if you look at this click and no click pattern, what would be the most natural thing for you to do? Well, so if this detector, one of the two detectors will never click. So if one of these two detectors click, you precisely know which phase pattern was presented, right? But then there is a probability that none of the two detectors will click because there's a probability of no click even here. There's a probability of no click even here. So e to the minus n is the probability that that neither detector will click. And if neither detector clicks, then what you have to do? Well, you have to make a random guess. And when you make a random guess, what happens? Well, you fail half of the time. Now, if you were to work this all out mathematically, you get the right answer, which is, I think you're converging on. It's e to the minus n. So B and D were the two closest answers. So really nice job on getting there. But you need that 1/2 factor because even when you do see no click appear in both detectors, there is still a probability that you randomly guess the right answer. And that's why you have that 1/2 factor. Okay, so let's do another example. Exact same concepts we are going to use. Okay, beam splitters, interference, photon detection, and probability theory. This time we'll look at a receiver for optical communications that is trying to tell apart between the symbols of what is known as an on-off keying modulation alphabet. on-off keying modulation alphabet is probably the most common form of modulation used in traditional laser communications. So we'll look at a pulse of light, which is either in vacuum, either in 0 or a coherent state alpha. Okay, so I've given you a promise. I'm going to hand you either 0 or alpha. And when I do give you alpha, the mean photon number is n, which is magnitude alpha squared. And I'm also going to tell you that it's equally likely that I'll give you 0 or alpha. And the question is, what is the average probability of error of choosing between the two on-off keying symbols using photon detection? That's the question. Okay, so you can start working on it right now. So that's the question. So the problem is very simple. So 0 or alpha, and you have a photon detector. So think about what would you do? So if you see a click, you obviously know that it must have come from alpha, right? But if you don't see a click, you don't quite know. So you have to make a guess. And when you make a guess, you might get it right, you might get it wrong. And if the prior probabilities of the two things are equal, then again, half of the times you get right, half the times you get wrong. Excellent, excellent. I think we can go ahead and stop the poll. So it was a simple question. So the correct answer is indeed 1/2 e to the minus n. Okay, so now the reason I wanted you to do this problem is because I want you to show something that might look entirely magical to even people that who are extremely familiar with classical laser communications. So remember this displacement circuit I had shown earlier? So if gamma is a coherent state that is presented to you, and if you want to displace it by beta, you can bring in a coherent state beta over square root of 1 minus eta and interfere it on a beam splitter of transmissivity eta much closer to 1. So you can take gamma to gamma plus beta. So let's say that this is a setup I'm going to use before I detect the on-off keying alphabet. So I'm presented with 0 or alpha, but you don't detect photons on it quite yet. You take 0 or alpha, so this gamma is either 0 or alpha. You don't know yet which one it is. Okay, but before detecting it, you shift it. You add beta to it. So if you had 0, after shifting your coherent state is beta. If you were given alpha, then your coherent state is now alpha plus beta. Beta is something you tune, but you don't yet know which one is it. And then you detect photons on it. Okay, so now what is the probability of error? I'm going to use the exact same rule as before. Okay, so meaning if I do not see a click, I'm going to guess it to be 0. If I do see a click, I'm going to guess it to be alpha. But now the probability of error is the probability of the first hypothesis times the probability I choose the second hypothesis given the first is true plus the other way around. This is a Bayes rule. So the prior probabilities are both half. But this time, notice here is that if beta was 0, this term was 0. So meaning this term is 0, meaning that if the first hypothesis is true, if this 0 is what is presented to you, you will never make an error, right? Because if 0 is presented to you in the normal photon detection, you will always get 0 click and you will make the right choice. But now, since I've moved it to beta, there is a probability that you will get a click from that beta. And that probability of getting a click is 1 minus e to the minus beta square from the 1 minus the probability of no click. So that's the probability you do get a click from beta. And so that is the probability with which you will make an error. So this term, instead of 0, this is now non-zero. But look at what happens to the second term. The probability of choosing a hypothesis 1 when 2 is true. So alpha plus beta. What is the probability you will make an error? You will make an error if this does not generate a click. So this term, instead of being e to the minus alpha squared, which gave you this 1/2 e to the minus n, e to the minus alpha squared, now it is e to the minus alpha plus beta squared. So if you take this whole expression and optimize or minimize this over the choice of beta, and then plot this probability of error as a function of n, the mean photon number of the original coherent state, you will get this line, this blue dash line. And I'm not writing an expression for this because the expression is too complicated. But you can, this is a very simple calculation you can do offline after this course is done. Try to just numerically optimize for beta and you will plot this blue dash line. And you see that this is better than what you get even with ideal photon detection, which is very interesting because what it is telling you is that if you knew what you are being presented with, if you know your task of telling apart between 0 and alpha, don't blindly detect photons on it, because photon detection must add that Poisson noise that is irreversible. But in this case, you are displacing the coherence that is present in you. You are doing some transformation in the optical domain, which is a unitary transformation. It's a reversible transformation. Just like you can go from gamma to gamma plus beta, you can go back from gamma plus beta to gamma. So you're doing this transformation and then detecting the photons. You can do better in this particular task. So this philosophy that you can, by doing some pre-detection optical transformation, you can dispose the information bearing light in a more favorable way to that noisy detection outcome that is yet to come. This is profound in many, many applications of photonic information processing with both classical and non-classical light sources. This black line that you see here is the minimum possible probability of error that is allowed by the laws of quantum mechanics. And we are going to derive it later in the last part of the course. So this is the right answer like you had derived, but this is not the minimum probability of error that is allowed by the laws of physics. You can do better. Okay, now going to part C. So I'm going to hand it over to Prajit at this point. I'll stop sharing my screen. And I suggest let's take a 5-minute break, and then Prajit, maybe you can share your screen and take over from here.
Sure. I think there was one question in the Q&A which I didn't answer, which is, can you recommend a textbook? Uh, and yeah,
I see. Okay, thanks, Prajit. Recommend a textbook for, was there a specific part of the lecture where that question came, Prajit? Let's see.
in the mode expression in the mode decomposition.
There are many textbooks on optics. There's a book by Gagliardi and Karp that is a beautiful book on optical communications that goes through modes and mode decompositions. There is set of lecture notes by Professor Jeff Shapiro in MIT's Open Courseware. The course number is called 6.453. That talks about the Kennedy receiver, talks about the beam splitter, talks about linear optical transformations. But I can't think of a single textbook that would cover all of the things that we are going through in this course. But please feel free to email me if you would like, and I'm happy to answer your question in more detail. If you have questions on very specific part that you wanted to delve deeper in, I can send you a reference. I say let's take a 2-minute break, and at 10 minutes past 5 p.m. Eastern, Prajit, you can go ahead and get started.
Sure.
Yeah, I suggest we go ahead and get started, Prajit.
Okay. So I will be covering part C of this course, which is on the quantum states of light. Here we will start with basic concepts of electromagnetic fields and give you a gradual introduction to field quantization and writing down the quantum states of the modes of light that you have been looking at till now. So uh, let's begin with a quick recap of Maxwell's equations. Maxwell's equations, when you write it in a source-free uh, set of in a source-free space in vacuum where there is no currents or no charges, take the following form, which relates the B field, which is the magnetic flux density field, with the E field, the electric field, and the H field, which is the magnetic field, with the D field, which is the electric displacement field. And the magnetic field and the magnetic flux fields and the electric field and the electric displacement field are related to one another through these constitutive relations, where these proportionality constants mu naught and epsilon naught in free space are respectively the permeability and the permittivity. And these two constants together define the speed of EM waves, and in this case, the speed of light by this relation. Now, it is also known from electromagnetic theory that the E field and B field will admit wave solutions. So let's take the E field and look at its frequency representation. Let us take an E field at some space point given by the vector r. So E field at x comma y comma z at a specific point of time t, and write down its frequency components by taking the Fourier transforms. So here I've written the E field as sum over its positive frequency components and its negative frequency components. Specifically, E plus is for the positive frequency components and the E minus is the negative frequency components. And then further, if I have to do a mode decomposition of this E field, each field component, E plus, the script T plus R omega, can be written down as a sum of the complex valued excitations of its different modes. So here you can see the summation where E plus has been written as script T times some complex valued amplitude A of omega for a specific set of mode functions, because I'm retaining the spatial description of the mode itself with the mode sum over all possible modes that I want to write down for the field. And the mode label small m is just an index that we will use to separate or distinguish between the different modes. And the scaling factor script t is just a constant that scales how big of a field you have or not. So the modes, again, just as Professor Saika discussed in the first part of the course, are just orthonormal set of functions dictated by the geometry. So if I look at the mode u m r of omega and I take its complex overlap with u k r of omega, so I take um star times u k r of omega, integrate over all the spatial coordinates. So the d3r is dx, dy, dz. I get the the Kronecker delta, which says that the two modes are orthogonal to each other if their mode indices do not match, or they're perfectly normalized, meaning that if I take the overlap of um with itself, I will get the number 1. So let's look at what possible modes you can write down based on the geometries. First, let's just look at free space where you don't have any restrictions on how the field can be. The easiest way to look at the modes of an electromagnetic field in free space are to write down the modes, is to write down the field in terms of what are known as plane wave modes. Here on your top left is the description of a single plane wave at a given frequency omega m. The way to interpret this equation, E plus given by these three components, is E of m will determine your polarization, direction, in which direction your field is oscillating. Omega m is your frequency, and this exponential with the k of m times the spatial coordinate r, spatial vector r, determines your propagation direction. So the frequencies in case of plane waves are continuous. Omega m can take any value because there are no constraints on what fields can be uh, or what modes can be excited for the free space electromagnetic field. So here on your top right is a small cartoon of what a EM field plane wave polarized along the y-axis looks like. Polarized along the y-axis looks like, and which is propagating in the x direction over here. So you can follow the blue arrow as it oscillates in the y direction. You can see roughly that the flow of energy is towards the x direction. And if you look at the B field, which is the red arrow, it is also a plane wave which is polarized along the z direction now, but also propagating in the x direction. We can then kind of switch up the geometry and ask what are the modes of some highly constrained systems, say highly reflective cavities. In this case, we can write down the total field of inside a highly reflective cavity in this form, where again, reminding ourselves, this is the complex amplitude, this is the oscillatory part, and this is the mode functions themselves. Now the allowed mode frequencies are discrete. So omega m cannot take any arbitrary value as they did for the plane wave modes. Why is this so? Because the highly reflective walls of the cavity will impose boundary conditions that constrain what frequencies are allowed inside the cavity. So if I take a cavity to be this a cube of side length L, then by the boundary conditions set by my mirrors, which kind of tell you what the turning point of the field is, the modes must satisfy these periodic boundary conditions, meaning if I shift my mode function by distance L along the x direction or the y direction or z direction, because it's a cube of side length L, they must remain the same because I'm essentially reflecting the field and I should not see any difference regardless of how much I shift. This will specify some requirements for the wave vector and say that the k of m that you choose for your wave vector can only be of the following form, where k of m now is 2 pi by L times some three constants, mx, my, mz, which are integers that will determine the overall mode index. So you can convince yourself by kind of substituting these k vectors back into an equation to see that this is indeed true and it satisfies this boundary condition. So um of r is the polarization vector times some exponent with these now three mode indices that you need to cover. And these will form a discrete set. This is a toy model of a cavity. In realistic conditions, you'll have to, you cannot necessarily write down mx, my, mz. So let's look at some more realistic cavity scenarios that you could potentially build in the lab. Firstly, because light is not confined along all three directions in realistic cavities, you can think of a plane parallel cavity. So this is a cavity which is just formed by two mirrors. Uh, the mirrors are on the XY plane, and you're trapping light in the Z direction. The gray boxes here are your mirrors, and the red region is where your cavity or your field is confined. In this case, the spatial mode can be, expressed in this form, where you have the polarization vector E of m, as well as something known as the transverse mode, which is a spatial function in only the x and y coordinates, so which is transverse to the direction that your field is confined in, as well as something known as the longitudinal mode or the longitudinal component of the mode. How do you interpret this? The longitudinal modes are modes with different frequencies, whereas your transformed modes are just orthogonal spatial functions or patterns. And when you work it out, and if you can just see this from the a simple example of a sinusoidal longitudinal mode pattern that I've given is that if I write down what the allowed frequencies are, then you will see a periodic comb-like pattern of frequencies that are allowed, which have a fixed mode spacing between adjacent peaks, where the mode spacing for a mode M and the adjacent mode, which is, let's say, M minus 1, follows the following relation with respect to the length of the cavity. So it's the frequency difference between adjacent modes is pi c over L. And if you write down, or if you want to draw out how the mode patterns will look like in terms of the field components, they look very much like standing waves on a string. So similar to the undergraduate physics example of a string that is oscillating between two fixed endpoints. In this case, the highly reflective mirrors will form the two fixed endpoints for your field. So you can take any one of these, 6 patterns or even more. I've only shown the first 6 of the longitudinal mode excitations that are allowed. And the transverse modes are not so intuitive without going into a more detailed derivation, but they can take a bunch of different bases. Here I show a specific Hermite-Gauss basis of showing orthogonal spatial mode patterns in the transverse direction. So these are modes for realistic cavities. How do we, use these, or how do we go on to writing down the quantum states of light for some modes that we will be presented with when we look at an actual experiment or we do a theory for. So the quantization of the electromagnetic field is something which is a very involved topic, but we will take a much less rigorous approach here and try to convince you that the rules we specify are sufficient to understand all the properties that we'll use in the rest of the course. So going back to the classical field description, we know that the electromagnetic field, or some component of the electromagnetic field, say the E field, has this description in terms of the modes, where, again, to remind ourselves, I have script T sub m as the scaling factor, the A of m as my complex mode scaling factors, or the complex amplitudes of the mode, the e to the minus I omega t, which is my oscillatory part, and the u of m, which is my mode functions themselves. In the classical field description, I have complete knowledge of the field if I know what the values of A of m are. Meaning, if I can specify all the complex mode amplitudes and for which modes they occupy. So I say that for a given u of m, the value of A of m is so and so. Then I have complete knowledge about the field, and I can, do any transformation detection or any other manipulation that you want to do with the field. However, in a quantum theory of electromagnetism, we don't have complete information about the modal amplitudes. In that setting, it is more natural to talk about the field in terms of its expectation values. And when we talk about expectation values of the fields, we have to say expectation values of certain operators of the field. So without getting into a nitty-gritty derivation of the electromagnetic field quantization, we will just think of quantization as a set of rules you have to follow, given to convert a certain classical field description to a quantum field description. So we will make some changes. So a classical field E R of t will become an operator, an electric field operator E hat R of t, which now has certain forms. So note that I have changed my complex amplitude from A to A hat. And I've also said that E of m has to have a specific form with E of m of omega. And what are these rules? So the quantization rules are the following. You take complex amplitudes to operators. So A of m of omega will become A hat m omega. So this is defined as a lowering operator. We will discuss what we are lowering later on. Similarly, the conjugate value of A star omega will become A dagger omega, which is defined as a raising operator. Again, what we are raising, or again, I write down the terms annihilation and creation, but we will get into what we are annihilating or creating later on. Uh, the simple rule here is that the complex amplitudes just become operators, as well as the operators must satisfy some canonical commutation rules. Meaning, if I take the commutator of A and A dagger, say in this case A of M, A hat of M, and A hat K dagger, sorry, A dagger K, the commutation is following. If I have two operators A and B, A hat and B hat, the commutator of A hat and B hat is A hat B hat minus B hat A hat, which I've written down here. The canonical commutation rule says that this commutator is not equal to 0 if the modes are the same. So if M equal to K, the ordering of how I write down the operator matters. I cannot say that A hat, A dagger hat is the same as A dagger hat, A hat. The amplitudes also take the specific form, which are now related to the frequencies as follows. And we can write down a Hamiltonian operator for the mode, which takes this following form. Now, if you are familiar with basic quantum mechanics, you will note that this Hamiltonian operator, or the total energy operator for the mode, resembles the quantum harmonic oscillator Hamiltonian, specifically the form h bar omega times A hat A dagger A plus 1 by 2 is reminiscent of a quantum harmonic oscillator Hamiltonian. And in the quantum harmonic oscillator, to those who are familiar, there is a ladder of energies that this oscillator can occupy, each separated by some separation, and we separated by an energy of h bar omega. But we will not assume that you necessarily know the quantum harmonic oscillator in great depth. We'll just go back and show you what does it mean to occupy one step of the ladder with a certain energy. So this motivates us to ask what, under the quantization rules, what states can these modes take? Specifically, we want to ask, well, what are the eigenstates or the states, eigenstates for the Hamiltonian operator? And for that, we'll show you how we come about with the states for that. So the eigenstates of the Hamiltonian operator can be derived roughly by noting a few things. We remember the canonical commutation rules, which says that A dagger commutator is equal to 1. So if I take a commutator of the Hamiltonian with the annihilation operator, I can work out that the commutator will be equal to h bar omega times the annihilation operator itself. Similarly, if I do the commutation relation with the A dagger or the creation operator, I'll note that the commutator is equal to h bar omega m times A dagger m. So if now say I have some state psi of the mode specified by m, and I consider an eigenstate, I consider that psi is an eigenstate of the Hamiltonian operator, meaning that if I apply the Hamiltonian operator on psi, I will get back a scalar value En in this case, let's say, with psi. This is true for psi. This relation is what I will say is required for the state to be an eigenstate. If I now apply the annihilation operator first and then the Hamiltonian on the state, from the commutation relation, you'll remember that HA minus AH is equal to minus H bar omega AM. So I can just move the AH component to the right-hand side and note that once again, I have the following relations, meaning HA times psi of M is nothing but the eigenvalue En minus H bar omega times the annihilation operator times psi of M, and Hm followed by A dagger on psi will be the eigenvalue plus H bar omega M times the creation operator times psi of M. Note that from this, A of psi and A dagger psi, A dagger ket psi are eigenvectors as well, with lowered or raised eigenvalues. So what do I mean by lowered or raised eigenvalues? Psi of m had an eigenvalue En when it was acted on by the Hamiltonian operator. When I apply the annihilation operator or the lowering operator Am on it, the eigenvalue is En minus h bar omega. And if I apply the creation operator or the raising operator A dagger, the eigenvalue is raised by h bar omega. So how do we now use these? How do we now use these relations to come up with the set of eigenstates? Well, I know that the difference between the two raised or lowered eigenvalues is h bar omega m from these relations. So let's say that I have some state psi 0 of m that satisfies a on psi 0 equal to 0. And let's say that the psi 0 is not a trivial zero state or zero vector. It's some realistic state. So if I now apply the Hamiltonian operator on the psi 0, I will see that h bar omega m is the energy is h bar omega m by 2. Forgive my typo here. There should be a psi 0 on the right-hand side as well here. So this means that with every application of the raising operator after this, I will add one step of energy equal to h bar omega m. So using this, you can define the ladder of the number states, or what we call in quantum optics or quantized fields, Fock states, which are defined as n for a given mode m, where n is some positive integer. The eigenvalue relation for the Fock state n is as follows. So if I apply the Hamiltonian operator on a number state or a Fock state n, I get h bar omega times n plus 1 by 2 n. This half factor is also known as the vacuum energy. And the action of the lowering and raising operators are as follows. So annihilation operator acting on n will take it down to take it down one step in the ladder to n minus 1 with a factor square root of n sitting in front of it. And A dagger acting on n will raise it up with a factor square root of n plus 1 sitting in front of it. So these are the Fock states or the number states of the quantized mode, or when we say that there is a single photon in the mode, it means that I have a single photon Fock state of the mode specified by the mode level m. For the first part of this course, you had been discussing what coherent states are. The coherent states are also the eigenstates of the annihilation operator. So if I have a state, say, which I label by alpha, which satisfies the following relation, meaning the annihilation operator acting on the state alpha will give me back the complex number alpha in front of the state. And they can be written, this is without proof, they can also be written down in terms of the Fock states as follows. This is a coherent state, and this is the quantum description of classical laser light. In an intuitive fashion, these are quantum states of light where the annihilation operator and the complex amplitudes are interchangeable. This is not a very physically correct way of thinking about it, because one is an operator and one is a complex value. But in some sense, I can treat the state in terms of completely its complex amplitudes, or I can treat the state in terms of its annihilation operator in an equivalent fashion if they're coherent states. So in the previous sections, when you had been looking at how these states interfere, say on a beam splitter, you had been treating their complex amplitudes. You had been modifying the alphas and the betas and saying that, okay, after a beam splitter, the alpha and beta combine in this format for interferences. When we look at interfering quantum states of light on beam splitters, say, we will now have to, we'll show that it's easier to treat them as evolutions of the operators rather than the amplitudes, because not all states are coherent states. So the number state of a mode, a single photon Fock state of a mode, uh, can now be specified in the following way. Given a mode phi of t, uh, which is this flat top mode that you had been looking at for the first part of this course, a single photon Fock state of this mode is written as 1 sub phi of t. And if I detect this mode with an ideal photon detector, what do we expect? We expect that there will only be one click because there is only one photon in it. But the time at which this photon will show up in the temporal extent of this mode from between 0 to t is a random time tau, whose probability distribution is given by mod square psi tau, which tells us now that unlike the coherent state, if I now take an n photon Fock state for the above mode, so if n of phi of t, uh, ideal photo detection over the entire temporal extent of the mode will produce precisely n clicks, but the click process is no longer memoryless. Why so? Because the moment I detect one click, I know that I'm expecting n clicks. So the rest of the time, I know that there are n minus one clicks, and that modifies my statistics of the state. So unlike the Poisson point process, the arrival of a single photon click in a time interval will change the probability distribution for the remaining clicks. So we will look at how number states are interfered on a beam splitter. A beam splitter in this case, instead of transforming the complex amplitudes as we had been doing before, a beam splitter can also be treated to look at the transformation of the annihilation and creation operators of two interfering modes. This is called the Heisenberg picture of quantum mechanics, where rather than evolving the quantum state of a mode, we will look at the evolution of the operators of the mode. So a beam splitter with a beam splitting ratio eta will transform a pair of modes A and B to modes C and D, where the uh, annihilation operators of C and D are related to the annihilation operators of mode A and B by the following relations. We know from 2 slides ago that n photon states in mode A have a ladder-like structure, and they have to follow these relations. So n photons in mode A is given by the following rule, where I have to apply the A dagger operator n times to get the n photon state. Similarly, we wrote down C and D in terms of A and B, but I can invert this transformation to write down A and B in terms of C and D by this relation to the right over here, the inverse transformation rules. So what happens when I excite the input modes in number states n and m? How do we write down the output state? Well, we know that n photon state of mode A will have the form that is given over here. So it's A dagger by square root of n factorial acting on 0. And similarly, I can write down m photon states on mode B as B dagger raised to m by square root of m factorial on 0, which is this form. So n photons in mode A and m photons in mode B can be written down in terms of the annihilation creation operators as follows. By the inverse transformations, I can translate the A's and B's into C's and D's and write down the following expansion. So now to write down this quantum state of mode C and D, all that I have to do is to expand these powers, so see and see what it looks like. Let's do some easy examples here. Let's say that I input one photon in mode A and no photons in mode B. So the state is 1, 0, where the first mode is A and second mode is B. I write down 1, 0 as a dagger acting on 0, 0 by uh, sending it through a 50-50 beam splitter. A dagger will become C dagger plus D dagger by square root of 2. And there is no B, so I don't have to modify anything there. And now applying C dagger plus D dagger by square root of 2 on 0, 0, I get this state, which is 1, 0 plus 0, 1 by root 2. So you can think of this as I'm splitting a single photon into one of two possible output ports. Uh, Similarly, if I start with the state 1, 1, I get A dagger, B dagger acting on 0, 0. Now A dagger will become C dagger plus D dagger by square root of 2, and B dagger will become C dagger minus D dagger by square root of 2. And if I multiply these two things, I get C dagger squared minus D dagger squared acting on 0, 0. Now note that I am splitting a photon coming in from A into two paths. I am splitting a photon from B coming in from B into two paths. But I don't ever get an outcome which is one photon each in two output ports. So this funny interference where if I send in one photon into both ports at the same time, resulting in all the photons coming out in one port or the other, is something that can be used to verify a single photon nature of light. So if I want to verify that for a given input mode, I do have a single photon state, one way to test it out is to take another single photon state and have them interfere on a 50-50 beam splitter. And if I don't see coincidences, meaning if I now detect both the ports on both sides, the zero photon state will produce no clicks. So I will either see two photons on one port and no photons on the other, or vice versa. I'll never see the case where it is one photon each in both ports. So this is if I were to if I were to ask to come up with a test of the single photon nature of a mode, I can use this property to test it out. This is also known as the Hongo-Mandel interference. Another thing to note here is that both of these states, the output state after sending in one photon into one port and uh, one photon each into two ports, are states which are not separable. I cannot write them down as some state of mode 1 tensor product with some state of mode 2. They always exist in a superposition of two possible states, and these are what are known as entangled states. And entangled states are very useful for a whole variety of reasons that we'll not get into here. But we will show how entangled states could be used. I don't think we go too much into the details of entangled states in this course, but we will show how entangled states can be used to read a bunch of different binary codes in a few slides succeeding this. But I just wanted to bring up this property that I cannot separate out the two states and write the state of two modes as a tensor product in this case. So they're known as entangled states here. So let's look at an example exercise of interfering number states in a beam splitter. So we split one photon across two ports. What happens if I split an n photon state of a mode uh, across two ports? So I in is n photons in the upper port and no photons in the bottom port. I send it to a beam splitter of transmissivity eta. What do I expect to see for psi out? Uh, Okay, I think we have a good set of answers for the polls. Uh, so one thing to note here is that any multimode unitary transformation of a single mode will generate entanglement across the different set of modes, which is something we showed in the previous slide with the single photon case and the single photon interfering across the 50-50 beam splitter case. In this example, the intuitive way of thinking about it is I am sending in n photons, which you can think of as n billiard balls, sending it towards the wall. And with the probability eta, the ball will reflect it, or with probability 1 minus eta, the ball will let it pass through. So the probability distribution of seeing k balls being reflected is given by a binomial distribution. And you can see that that is true for option B here, where with a binomial distribution is given by this n choose k, eta raised to the k, 1 minus eta to the n minus k photons going through mode 1, which is corresponding to k billiard balls being reflected, and n minus k going out into the other port. So that's the correct answer. I can't seem to get rid of the poll, so give me a second. Oops, sorry. Yeah, that was not helpful. Sorry about that. Pretend you didn't see the answers. Uh, so let's go back to that example of one photon in one input port and zero photons in the other input port, and now send it through a Mach-Zehnder interferometer for an application. Here I am trying to read phase-coded information using the number states. So again, in the first 50-50 beam splitter, I have one photon in one port and zero in the other. After they go through the 50-50 beam splitters, I know that the state is 1, 0 plus 0, 1 by square root of 2. And now they encounter two phases. The upper port will see a phase theta 1, and the bottom will see a phase theta 2. Theta 2 is fixed to 0. Theta 1 can be 0 or pi. This is similar. This is a similar example to what you saw for the coherent state case, but now I'm using single photon states. After it goes through those phases, I either have the state 1, 0 plus 0, 1 by square root of 2, or I have minus 1, 0 plus 0, 1 by square root of 2. What is the probability of error for choosing between the two phase patterns if I now were to perform ideal photo detection on the two output ports? I guess as people are answering, the way to think about it is if I send in the 1, 0 or 0, 1 back through that beam splitter, I expect the pattern 1, 0 plus 0, 1 by square root of 2, or 1, 0 minus 0, 1 by square root of 2. So if I take the superposition 1, 0 plus 0, 1 by square root of 2 and send it forward, I'll either get 1, 0, or if I take minus 1, 0 plus 0, 1 by square root of 2, I get the pattern 0, 1 on the output. So I only have two possible outcomes, either the upper detector clicks or the lower detector clicks. I never have the case where neither detectors don't click, or I don't have the problem with coherent states where I get the no click outcome, which will give me a probability of error and I have to guess randomly. So the correct answer, as some of you have answered or seen due to my mistake, is that the probability of error is 0. So this is very important because, as you saw with coherent states, which are classical states of the mode, the probability of error was never 0. And so if I had an ideal single photon state in a specific mode, I can read between the two phases, 0, 0 or pi 0, with zero probability of error if everything else was perfect in the system. And this is a result that you can extend to read an arbitrary number of bits with zero probability of error. So here is an example where rather than encoding two possible phase patterns, 0, 0 or pi 0, I'm encoding k possible phase patterns through these boxes, which are either phase 0 or phase pi. So the way to read this information is to take a single photon state, split it into two modes, and then split it further into k modes by dividing it on the 50-50 beam splitter again. Because I will get an equal superposition of the photon being in one of the k modes. So I get patterns like 1, 0, 0, 0 plus 0, 1, 0, 0, 0 plus 0, 0, 0 and one photon in the kth mode. I can now have these photons pick up the different phases, theta 1 to theta k, and re-interfere. And at the very end, based on what combination of phases were used, one of my k detectors will click. And again, you can show, if you work it out, that the probability of error in determining what phase pattern you had encoded is 0. So which means I can read up to log 2k bits of information with zero error of probability. This is something that Saikat and Jeff Shapiro showed in a paper in 2013, which is referenced over here. Achieving the zero error probability for detection is not possible using any classical light probe, including coherent states. So that concludes my section. Go on, I'll pass it back to Saikat.
Okay, all right. Thanks,
Uh,
Prajeet. I
Give me a
am going to.
second. I have to. Uh, yeah.
Yeah,
For some reason the polls don't go away for me when they appear, so I have to leave the presentation mode. Yeah.
sounds good. I'm going to reshare my screen. Okay, so before I go into this last section of the course, let's recap some of the most important things that that Prajeet covered. So beginning of the course, we talked about modes. Modes are like buckets into which you put complex amplitudes, and that part B was all about complex amplitudes of a set of modes, which now we have a name for. It's a coherent state of a set of modes. We also said that coherent state of a set of modes can always be written as a coherent state of a single mode and vacuum in all the other modes that are orthogonal to that mode. We talked about how coherent states mix on a beam splitter. When two coherent states meet on a beam splitter, you get two coherent states, independent tensor product. Coherent states are the output of that beam splitter. And that's a property that is unique to coherent states. And then we talked about how if you detect photons on a coherent state, you get a Poisson point process. You get a random outcome and that random outcome has a statistical description. And then after that, we talked about other states of light, and Prajeet walked you through a description of field quantization, where he said that for classical light means once you've identified the set of modes, you have to talk about either the set of complex amplitudes of those modes or a probability distribution over those complex amplitudes. In the language of quantum optics, the former is a pure state, it's a coherent state, alpha 1, alpha 2, alpha 3, alpha 4 of those modes. In the language of quantum mechanics, for those of you who are familiar, statistical light is a mixed state. It's a mixture of tensor products of coherent states. Okay, and that's all classical light. For quantum light, as Prajeet said, that once you have identified the set of modes, you have to talk about the quantum state of those modes. And talking about quantum states of a collection of modes, we first derived what are number states of a mode. A number state of a mode has a fixed number of photons. So when you detect photons, you get an answer with certainty. And then you saw when you have number states meet on a beam splitter, even if at the input of the beam splitter you have a tensor product state, you have number state 1 and number state 1 at the two inputs. At the output, you get an entangled state. You get a state that cannot be written as a state of this mode and a state of that mode. You have to talk about the state of the whole collection of modes. And that's a property unique to non-classical states of light. You already saw some examples of where number states of light can do better than coherent states of light. Now, one of the things that we did not say, and this is out of scope from this course, is that any quantum state of a mode can be written as a coherent superposition of number states. So if because why is that so? Because number states, if I take number states from 0 to infinity, that spans all the possible energies of a mode. And any two number states are orthogonal with each other because you can tell them apart perfectly. And hence they form a basis. So they form a basis, meaning any quantum state can be written as a superposition of those states. All right, so with that, I think we are going to now go into the last part of the course where we will look at a few applications of what we have learned. And I have chosen state discrimination as application direction, just so that because it brings together some of the things we have learned on transformations and quantum measurements, but there's a whole slew of applications of what you have learned in this course, which I'm happy to go into later if you are interested. And it's a vast area, which I hope that at the end of this course, the material you learned will enthuse you to learn more, to get into photonic quantum information processing, which is this broad area. Okay, so again, because I'm assuming that you have some exposure to quantum optics, or quantum mechanics, I'm going to assume that you have seen measurements in some form or the other before. A pure quantum state, which I'm writing here as psi, when subject to a projective measurement. The projective measurement, the most general projective measurement, is describable by a set of unit norm orthonormal states or orthonormal kets, vectors. These WKs, they are orthonormal in the sense that if I take any of these two WKs, their inner product is equals to the Kronecker delta function. This inner product is not the same inner product as the inner product of mode functions. This is an inner product of two quantum states. We'll see a little bit more of that later on. So if psi is subject to a measurement described by these orthonormal vectors, orthonormal states, WK, then you get an outcome K with a probability given by the magnitude squared of psi inner product with WK. And because these WKs, they form a set of orthonormal vectors, it's easy to see that these probabilities must add up to 1. So just with that information, we are going to do a derivation that I will use to walk you through a set of examples to show you how to even find out the minimum possible probability of error of telling apart between two coherent states. You might remember this example that we did in 2 sections prior on discriminating between on-off keying. Remember, we talked about telling apart between 0 and alpha. When you did photon detection, you found probability of error was 1/2 e to the minus n. And then we evaluated the probability of error for the Kennedy receiver, where we first displaced and then detected, and you were able to do better. And then I left as a mystery this plot of the minimum possible probability of error of telling apart between 0 and alpha. This slide, we are going to see how you derive that minimum possible probability of error of telling apart between two states that have some inner product. So let's begin by taking the two states psi1 and psi2, and let's say that the prior probabilities of the two states are p and 1 minus p, and that's known to you. So you have psi1 with probability p, psi2 handed to you with probability 1 minus p. And you have to pick a measurement that minimizes the average probability of error. So psi1 and psi2 are two states that are completely described by the inner product between them. So the inner product between the two states, psi1, psi2, I'm going to call it sigma. And for ease of description, I'm going to assume that sigma is a real number. Okay, so it's a real valued inner product. So when you have two unit norm vectors with a real valued inner product, you can embed those two unit norm vectors on a plane, right? You can just put it on the plane of your of this whiteboard. And once you have done that, then the act of choosing an optimum measurement is to choose how you orient two other orthogonal vectors with respect to the state vectors. But before that, let's set some nomenclature. Okay, so once I have drawn two vectors with some angle between them, I can always call that angle 2 theta, so that the inner product is a cos 2 theta, right? I can write psi1 as cos theta sine theta and psi2 as cos theta minus sine theta by just picking an appropriate x-axis and a y-axis. So the x-axis is 1, 0, the y-axis is 0, 1. I'm going to call this 1, 0 as a 0 vector and 0, 1 as the 1 vector. So 0 and 1 are two orthogonal states. And psi1 and psi2 are these two, two element vectors. Now, once I have written it this way, I've chosen my x and y axis. My job is to pick W1 and W2. W1 is the measurement vector corresponding to state psi1. And W2 is the measurement vector corresponding to state psi2, meaning when I subject that unknown state, which is either psi1 or psi2, to the measurement gadget, I will get an answer W1 or W2. And the W1, W2 has to be at 90 degrees with each other because these are measurement vectors. So our job is to pick how to orient the measurement vectors with respect to the state vectors such so as to minimize the average probability of making an error. So the only thing that's undetermined in this whole thing is this angle phi, right? So this is the only thing which you need to find out. If you find phi, then you have set the measurements. And if I write down this phi, then you can clearly see I can write W1 as cos phi sine phi and W2 as sine phi minus cos phi because they are 90 degrees with each other. So we have done everything that was needed. The rest is trivial. So the rest is, I'm going to call the measurement results 1 and 2. W1 for 1, W2 for 2. What's the probability of picking W1, of seeing the W1 outcome, when you present the measurement gadget with the state W2? That's given by the mod squared of W1 psi2 squared, right? So if you work out the mod squared of W1 psi2 squared, so the inner product between this and this, it's easy, cos theta, cos phi, cos theta minus sine phi, sine theta whole squared. Just some basic trigonometry. It's cos square of theta plus phi. Similarly, probability that you will choose 2 when 1 is fed through the measurement gadget is given by this expression. So the average probability of error is the probability that hypothesis 1 is true, which is P, meaning the state is psi1, times the probability that the measurement gadget picked the wrong outcome given that hypothesis 1 was true. So P of 2 given 1 plus the other way around. Higher probability that hypothesis 2 was indeed true times the probability that you made an error conditioned on the fact that hypothesis 2 was indeed true. So you can substitute these expressions and you get an answer. You get some probability of error, which is just a function of phi. Theta is known. So how do we find the minimum probability of error? Well, you differentiate it. You differentiate this probability of error expression with respect to phi and set it to 0. See if you can, this is very, very basic, just differentiation and a few lines of algebra. See if you can work this out and tell me which one of these is true. The optimum value of phi satisfies which one of these these four equations. So all you would do is that take these two expressions, put it into this formula, differentiate with respect to phi, and see if you can find the right answer. It's just a few lines of algebra here to work it out. Okay, I suggest that we go ahead and close this poll because this is mostly just algebra workout. But I'm glad to see that the majority got the right answers. It's the relationship is tan to phi equals to tan to theta over 2p minus 1. Now, if you take this relationship between phi and theta and plug it back into the expression for the minimum probability of error. So if you take this and put it back into the minimum probability of error, you get this formula. And this formula for the error probability, it works both ways. Probability of H1 when Z is 2 and probability of H2 when Z is 1. And probability of correct decision is just 1 minus this, which is just minus sign becomes a plus sign. So when the priors are equal, when P and 1 minus P are equal, the probability of error, minimum probability of error formula just becomes 1/2 times 1 minus square root of 1 minus sigma squared, where sigma is the inner product between the two states. So this is the formula that is known as the Hellstrom bound, or the minimum probability of error of telling apart between two quantum states, two pure states. So with that, let's go back to where Prajit stopped in discussing non-classical states of a mode, number states of a mode. So number state n and number state m, if I give you a mode which I excite in either number state n or number state m and present it to you, what would you do to tell it apart? Well, you would do photon detection, right? If you do photon detection, you will distinguish between them with zero probability of error because the two options will generate different number of clicks if you had ideal detectors. And we have already seen in the previous slide, this formula, that the only way you can have this probability of error to be zero is if the sigma is zero. If the sigma is not zero, this probability of error will be greater than zero. So sigma is zero means the inner product between n and m is zero. So the number states must be orthogonal states. Now, of course, you derived number states to be orthogonal states because they were eigenstates of the Hamiltonian that Prajit talked about. But this is another very simple way to see it from the state discrimination theory. Now, because number states of a mode span all the possible energies a mode can have from 0 to infinity, and they are orthogonal states, meaning they form a basis. So it's reasonable that they must form a basis to represent any quantum state of a mode. So any quantum state of a mode, a squeeze state, display squeeze state, coherent state, number state, single photon Fock state, any quantum state of a mode, any pure state of a mode can be written as a superposition of number states because number states form a basis. Now, the coherent state of a mode, as Prajit talked to you about, is hence also a superposition of the number states. And we saw this expression earlier. And now you can see from a more formal perspective why, when you do photon detection on a coherent state, you get Poisson statistics. Because if you were to present that coherent state to a number measurement gadget does measurements whose measurement operators are the number states. And hence, the probability of getting answer n, P of n, is equal to magnitude squared of n alpha inner product. And magnitude squared of n alpha inner product is the Poisson distribution. So e to the minus magnitude alpha squared, which we called n earlier, times n to the little n divided by little n factorial. Okay, so in the next slide, we are going to calculate the inner product between two coherent states, our on-off keying alphabet example that we considered in exercise 5. And we will see how we get the minimum probability of error from there. So this is an exercise, a very, very simple exercise. I'm not going to stop for too long here. So I'm going to have you calculate the inner product between two coherent states, 0 and alpha. So 0 is both a number state and a coherent state. And we have already written the coherent state in the number basis here. So this is, I've given this expression to you. And I would like you to calculate the inner product between 0 and alpha. So just take 0 from this side. So calculate 0 alpha and take 0 on the other side and tell me what you get. And remember, when you calculate this, that 0 is both a number state and a coherent state, which is a beautiful thing about this, what we call the vacuum state. So let me take a few seconds and see how many people get this right. So go ahead and Brianna, start the poll. Oh, sorry, I hadn't shown the options. So remember, I'm just asking you to calculate the inner product. There's no probability of error or anything right now. I'm just saying I'm just asking you to calculate 0 alpha. That's it. 0 alpha, meaning you're going to put 0 over here on this side. So when you put 0 on here on this side, the only term that's going to survive is when n equal to 0. And then when n equals to 0, what do you get? You get e to the minus alpha square over 2 times alpha to the 0 over 0 factorial. Okay, we can go ahead and close the poll. I have enough answers here. The correct answer is e to the minus n over 2. Excellent. So very simple calculation. But why did I have you do this calculation? Well, because we know that if I give you two states, and if you know its inner product, so inner product between 0 and alpha is e to the minus n over 2. You just derived it. Then from that simple one-page few lines of theory, you calculated the quantum limit of the minimum probability of error allowed by the laws of physics to tell apart between 0 and alpha, if they are equally likely. And that is 1/2, 1 minus square root of 1 minus sigma square. If you substitute sigma equal to e to the minus n by 2, you get this black line. Seems like magic, right? I mean, you calculated without even prescribing the receiver. We calculated in just a few lines, what is the minimum possible probability of error allowed by the laws of physics to tell apart between 0 and alpha? We had already calculated before that direct detection gives you this probability of error if you just blindly detect photons, which is how things are done right now in an optical communication system using on-off keying. If you use the Kennedy receiver, which applies a displacement before detection, you get this blue line, better performance, and this is the best performance you get. Now, there is a receiver prescription that was invented by Sam Dolinar back in 1973, which exactly achieves this minimum probability of error for two coherent states of light, tell apart two coherent states of light. And I will not have time to describe this receiver in detail, but the way it works is that you feed the electric field, the pulse, excited in either coherent state alpha or 0, this mode, flat top mode, let's say I'm showing excited in 0 or alpha, into the receiver. The receiver doesn't directly detect photons on it. What the receiver does is that it applies a displacement field like the Kennedy receiver, but it's a time varying displacement. I'm showing here L1t and L0t. And it's that displaced field, ST plus Li of t, is what it feeds into the detector. So the detector generates a Poisson point process whose rate function is the mod squared of this time varying amplitude. And then every time the detector sees a click, it's flip-flops between applying either this displacement signal or the other displacement signal in this adder. And at the end, once the whole time has passed, the entire pulse has been eaten through, the detector just declares its current hypothesis. So it was flip-flopping between hypothesis 1 and 2 as the final verdict. And by choosing L1 and L0 appropriately, Sam Dolinar proved that this receiver on an average would achieve this Hellstrom bound, this minimum probability of error. So this derivation of this receiver itself is the subject matter of a 200-page PhD thesis from MIT's 1973. But interestingly enough, this receiver prescription does not generalize to telling apart between more than two states of light. We don't even know how to write down a receiver right now that can tell apart between three coherent states with the minimum probability of error. Another thing I want to mention here is that in discriminating coherent states, we talked about modes for most of the initial part of this course, right? And then now we are talking about states and inner product of states. One thing that you should remember that these two inner products we are talking about in the same course, they are in different Hilbert spaces, they're different spaces. The inner product of modes was this integral of psi1, psi2 star dt. That inner product is an inner product in the L2 norm vector space spanned by square normalizable functions. The inner product of quantum states like alpha and beta, the inner product between two coherent states, this expression, this inner product is an inner product in the Hilbert space spanned by the Fock states of a mode in which any quantum state of a single mode resides. And something that is insightful to see is that if I give you two coherent states, they can never be told apart with zero probability of error, right? Because inner product between two coherent states alpha and beta is never equal to zero. So two coherent states, if I give you a mode excited in coherent state alpha or coherent state beta, no matter how you design your receiver, you will always have some probability of error. And even if they are excited in two orthogonal modes. And why is that? Well, let's say that I have two modes, phi1 and phi2. And I excite under hypothesis 1, the phi2 mode in coherent state alpha. So this is the phi2 mode. And phi1 mode, I leave unexcited. And under hypothesis 2, I excite the phi1 mode in a coherent state beta, and I leave the phi2 mode unexcited. With the Hellstrom bound theory, we can calculate the inner product between psi1 and psi2, the two hypotheses. And as you can see, it's the inner product between these two tensor products, zero inner product beta times alpha inner product zero, which is also not zero, it's greater than zero. Hence, the probability of error is not zero. So again, if I give you two modes that are orthogonal, and I give you an electric field that lives in a superposition of those two modes, you can separate the two modes physically. That's what was mode sorting. But if I give you a mode or two modes or three modes, and I excite them in a coherent state, alpha 1, or a coherent state, alpha 2, or a coherent state, alpha 3, from a library of possible coherent states and ask you to tell apart which of the hypotheses was presented to you, that task cannot be done with zero probability of error. But that task can be done with zero probability of error if those modes were excited in number state, because you can just do photon counting. Okay, so I hope this was clear. This was a very important thing to understand. And this whole theory of Hellstrom limit calculation extends very naturally to discriminating between M states. Again, the concept is very similar. I'm going to leave the derivation to a beautiful paper by Horace Yuan, Bob Kennedy, and Lax, 1975. There is also the derivation of this appears in Hellstrom's book on quantum detection and estimation theory. So state psi I, prior probability pi. Now, instead of a single inner product, you have all of these n choose two inner products, m choose two inner products. M is the number of possible states in the library. So these sigma ij's, they define the geometry of these states with respect to each other. The matrix of these inner products is known as the Gram matrix. The measurement vectors, wj's, corresponding to the jth state psi j. Your job is to find the measurement vectors that minimize the probability of error. So what you're trying to find really is the relative orientation of those measurement vectors with the state vectors. So if you remember a few slides back when you calculated that phi by differentiating PE with respect to phi, what you were doing is that you were orienting W1, W2 with respect to psi1, psi2. Now you have M state, psi1, psi2, psi3 up to psi m, and you're orienting an M element unit norm constellation of unit vectors with respect to those state vectors with an objective of finding the minimum possible probability of error. This is the minimum, this is the probability of error. Why? Because it's a 1 minus the average probability of a correct decision. This is the probability of correct decision because this is a prior probability that the psi I state was presented to the measurement gadget times the probability that you made the right decision, which is the magnitude squared of Wi psi I whole squared. And magnitude squared of Wi psi I squared is something I'm going to name as xii. So xij is the inner product between Wi and psi j. So if you can find all these xij's, meaning how the measurement vectors are oriented with respect to the state vector, so this xij's that are m squared elements, m by m matrix, then your job is done. So Yuan, Kennedy, and Lax, they solved this problem using Lagrange multiplier methods. And they found that if you are given the PIs and the sigma ij's, the problem is described by the priors and the Gram matrix, then if you can find the solve this m times m plus 1 over 2 linear science equations, you can find a solve for the xij's and plug the xii's into this equation to get the minimum probability of error. So I am not going to derive for any more constellations, but you can go ahead and derive it for, say, minus alpha, 0, and alpha. So now you have a 3 by 3 gram matrix, or quadrature phase shift keying, which are these 4 coherent states, or pulse position modulation. This is a very common modulation format used for deep space communications, where you have these as 4 modes. You can think of these as 4 time bins. These pixel modes, like we talked about in the beginning of the course, and you excite only apart between these 4 coherent states. And even for any one of these cases, you can calculate the YK limit, the minimum probability of error, but no known conventional optical receiver design, even when they are operating at their quantum noise limit, can achieve the performance predicted by that YK limit. So the receiver that attains the Hellstrom bound is no longer the Dolinar receiver. The Dolinar-like receiver doesn't work for more than two options. If I have 3, 4, any more than 2 options, it doesn't work. And the receiver that does attain the Hellstrom bound must use quantum transformations of coherent states prior to detection. You know, you saw how the Kennedy receiver applies a displacement before detection, and that improves the probability of error. The Dolinar receiver also applies a displacement before the detection, but it keeps changing the displacement. But the displacement is a classical operation. You can realize a displacement by a beam splitter and a coherent state, like we saw in the very beginning of the course. So that philosophy still carries on, that you have to do something before you detect, but that something cannot be classical anymore. You have to use some quantum pre-detection, and we will not have enough material quantum transformations, but squeezing, which can be realized by passing the light through a nonlinear optical crystal. An example of such a non-classical transformation of light. Position modulation. So this is an example that I was showing. So 4 time slots, and you are exciting only one of. Easy to see what is the probability of error of discriminating between these PPM code words when you just use photon detection. This is an extension of that problem we did on on-off keying. So if you detect photons on all 4 of these pixel modes, if you get a click in the pulse bearing mode, you will make the right decision. If you don't get any clicks in any one of these 4 modes, then you don't know what to do. You'll have to make a random guess. The probability that the pulse bearing mode will miss a click is e to the minus n. That times a random choice giving you a wrong answer is m minus 1 over m. So this is the average probability of choosing the option incorrectly. Now, this exact format was used by MIT Lincoln Laboratory in the 2013 lunar lasercom demonstration program, where they set up a laser communication link between the moon and Earth. They use pulse position modulation signaling with a photon detection on the Earth station. If you solve the YKL conditions, it's actually very easy to go through this calculation. And even though I'm not leaving it as a problem, I would encourage you to go through these calculations, because the gram matrix is extremely simple. Any pair of the PPM code words have the same inner product. So the XIJs are very easy to work out. If you work out the YKL conditions for the minimum probability of error, you get this more complicated expression. But you can see that this expression goes as e to the minus 2n instead of e to the minus n. So if you were to sketch it out, the probability of error versus n, this red line is direct detection, whereas this blue line is the Hellstrom limit. And even to this date, we don't know a receiver design that actually achieves this blue line exactly. But there are receiver designs that use classical pre-detection transformations. For example, something that we talk about in this paper based off of some work that Dolinar did in his PhD thesis, and which we implemented in an experiment in this 2012 paper, which can get close to the Hellstrom limit when n is high, but it doesn't get close to the Hellstrom limit when n is small. So this problem of finding receiver designs that get to the quantum limit is still open. So and you are already starting to see a pattern of the importance of treating light quantum mechanically, even when the light that you're working with is classical. Even when we are talking about coherent states, it's important to treat the coherent state as a ket, as a coherent state, as opposed to just a complex number, because it gives you this beautiful insight on what's the best possible thing, but what's the best possible performance you could get in a particular information processing task, like state discrimination, or like resolving two stars, or finding the best possible beam deflection measurement. There's a whole host of tasks that light is used for, where light carries the information. But in order for you to find out the best possible performance that the laws of physics allows you, you have to treat that light as a quantum mechanical object, and then use these tools from information theory, estimation theory, detection theory that tells you the best possible performance you can get. And that part is typically the easier of the two tasks of finding an actual receiver prescription or actual system design that gets to that fundamental limit. So in both of these examples we talked about, we found the minimum probability of error very easily, but finding a receiver that can use things we know how to build in the lab, like beam splitters, phase shifters, squeezers, detectors, photon detectors, number states, feed forward, that achieves that minimum probability of error. That's typically the harder step. One last example, and I'll close the course after this. This is you are now seeing 8 code words. Okay, so a code word is just a word we use for communications, where you have a set of time bins that are populated with coherent states. And here I'm just giving you these 8 states that are tensor products of alphas and minus alphas. And there are 32 possible code words, right? If each pulse has 2 options and I give you 5 pulses, 5 time bins. But of those 32, I'm only saying that 8 of those 32 are allowed. So these 8 code words comprise what is known as the code book. So if I give you this code book of binary phase shifting modulation, or BPSK modulation coherent states, and I tell you what is the minimum probability of error of telling apart between these 8 possibilities? Well, you can work out the YKL conditions. And you can look up this paper, the first one that solves those YKL conditions. And we can plot the probability of error of telling apart between these 8 code words as a function of n is mod alpha squared, and you get this pink line. And now you are thinking, how do I design a receiver that gets you the pink line? So what was the first obvious idea that comes to your mind? The first obvious idea is that, well, now I have 5 time bins that will come one at a time. I know that for every time bin, there will be either alpha or minus alpha. So shouldn't we take the Doliner receiver that can optimally tell apart between alpha and minus alpha and use that for each of the 5 time bins separately? So first time bin, I say alpha or minus alpha, second time bin alpha or minus alpha, and so on. And then take that outcome and then use maximum likelihood discrimination, that is the best possible classical estimator, to tell which of the 8 code words from the code book that did we receive. Well, turns out if you did that, you will get a probability of error that is given by this blue dashed line, the blue dotted line, which is not quite where the pink line is, which tells us that in order for you to get to the minimum possible probability of error of telling apart between these 8 code words, you need a receiver that collectively acts on all the 5 time bins. And such a receiver is known as a joint detection receiver, a receiver that collectively acts on these 5 kets, these 5 coherent states, in a way that doesn't even have a mathematical or a physical prescription of acting independently on one of those 5 time bins at a time, or one of these 5 modes at a time. So this is the analogous thing to entanglement that Prajit talked about. So entanglement is to states as joint detection is to measurements. So an entangled state of 2 modes, you can't talk about the state of the first mode and the state of the second mode. A joint detection measurement of 2 modes cannot and does not have a representation or does not have a realization of a measurement that acts on the first mode and then acts on the second mode. It must act collectively on the 2 modes. So this paper talks about how you can realize such a joint detection measurement using a very small 5-qubit quantum computer. And this paper, we tried out a very simple instance of that circuit in an actual trapped ion quantum computer with the help of some colleagues at Honeywell, and showed that it actually, the main idea behind it works. Well, with that, I would like to close the course. So I hope that you got the main message behind this course, that why should we care about a quantum description of light? And the fact that when we write the state of an optical field in the quantum language, it allows us to evaluate the fundamental limits of precision of information processing was hopefully made clear. And once you do that, finding actual designs of transmitters, modulation formats, receivers, etc., that meets those quantum limits is typically a hard task. And many, many problems are still open in the field. And there are many applications of both quantum states of light and quantum measurements and quantum transformations. This is just a partial list. We have talked about quantum receiver designs. I did say a little bit about squeezed light. One of the most pronounced and prominent and famous use of squeezed light has been in its use in increasing the sensitivity of in the laser interferometer gravitational wave observatory, the LIGO observatory, which detects huge gravitational events far, far away with very high precision. Using a squeeze light can also enhance the sensitivity of detecting radio frequency photonics using RF photonic antennas. Using photons to generate entanglement between quantum memory banks, for example, prepared using silicon vacancies in diamond, which you will hear about in other courses in this series, is also something that utilizes principles of quantum optics. And those become the tenet of quantum internet, which is the underlying subject matter of research in the Center for Quantum Networks. And once you have generated entanglement, distant entanglement between quantum memory banks that are situated many, many, thousands of kilometers away, for example, then such distributed entanglement can then be used for many applications, including, for example, enhancing the resolution of a collection of distant astronomical observatories that are equipped with entanglement across them, as opposed to just classical collaborations. So with that, I will close the course, and happy to take any more questions. And don't forget to fill out the course evaluation survey. So if there are any chat questions at this point, I'm happy to take them. So let me stop sharing my screen here so I can look at the chat questions. Okay, looks like Prajit has answered most of them.
I think the last one is, can superposition of coherent states be orthogonal? I was just writing out an answer, but if you want to tackle that, yeah.
What's the question? Can superposition of coherent states be orthogonal? A very good question. Absolutely, they can. And you know what an example is? We talked about alpha and minus alpha towards the end of the course, binary phase shift keying. If you write down a state alpha plus minus alpha, which is a superposition of those two coherent states. But remember that you can't just write alpha plus minus alpha. You have to put a normalization constant in front of it to make sure that it's a properly normalized state, meaning inner product of the state with itself is 1. And then define another state, which is alpha minus minus alpha. That's also a superposition of two coherent states. And also you have to put another normalization constant, which will be a different one from the first state's normalization. These two states are orthogonal to each other. And these two states have a name. They're called cat states. In fact, alpha plus minus alpha and alpha minus alpha, these two states that are orthogonal to each other, they have a use in encoding information, encoding quantum information. And this particular way of encoding a qubit, which is a two-level quantum system, into these two orthogonal states, have certain pros and cons with respect to encoding a qubit in, let's say, Fox states 0 and 1, or other forms of encodings. So coming back, so absolutely, even though two coherent states themselves are not orthogonal, you can create superpositions of coherent states that are orthogonal to each other. And hence, there must exist a receiver that can tell apart between those two cat states. And for those of you who are curious, the Dolinar receiver, which was originally invented for telling apart between two coherent states at the minimum probability of error, also applies for any two quantum states of a mode that are including, for example, the telling apart between two cat states. But that extension was invented many years later. But going beyond two states in a library and getting the minimum probability of error is hard. Any more questions? We officially have until 6:45, so we can take a few more questions in the chat window. All right, if not, Brianna, go ahead if you have any final closing comments and instructions for the course evaluation survey, please.
Okay. Thank you, Saika and Prijit, for taking your time to teach this course. As our participants log out, you will get a pop-up with our post-course survey. If you could take a moment to take that. And then in the coming weeks, we will get out the recording of the lecture as well as the slides. So other than that, that is all I have. So thank you for your time.